Good morning, sir.
Morning, madam. Is my voice audible?
Yes, sir. It'll start. Good morning to all the dignitaries, faculty members, and participants. We welcome you all for. We welcome you all for today's session on quantum linear algebra and optimization. It's my great pleasure and privilege to introduce our esteemed resource person for today's session, Dr. Kupuswamy. Dr. Kupuswamy is currently serving as a professor in School of Computer Science and Engineering at Vellore Institute of Technology, AP University. He is an IEEE senior member, IIEC member, innovation ambassador, and also Coursera certified in machine learning. His research interest includes machine learning, Internet of Things, networks, and smart device applications using sensors, Raspberry Pi, and Arduino technologies. Dr. Kupuswamy has contributed as a reviewer for reputed international journals. Academically, he earned his bachelor degree from University of Madras, completed his master degree in computer science and engineering, and PhD from Anna University. He has published more than 80 research papers in leading international journals and IEEE conferences, and also authored a book in the field of computer science and engineering. With his vast academic experience and strong research contributions, today's session will certainly provide us with valuable insights into fascinating domain of quantum computing and optimization. On behalf of everyone present here, I extend a warm and hearty welcome to Dr. Kupuswamy. Welcome, sir. Now I kindly invite Dr. Kupuswamy to deliver his expert talk. Please, sir. So now it is not audible. 1 second. Sir, not able to hear. Not able to hear. Sir, not able to hear. Able to hear my voice?
Ma'am, your voice is audible, ma'am.
Yes, sir.
Things.
Yes, now able to hear, sir. Thank you, sir.
No,
You
no,
may
ma'am.
proceed.
Ma'am, myself Nagraj, ma'am. Sir
Oh,
voice not able to audible.
okay. Kupuswamy, sir. So, sir left the session.
Madam, is it audible now? Hello?
Yes, sir. Now audible. I'll
Yeah.
make you host.
Yeah.
1 second. In what name has joined?
Kupuswamy, madam. Learn and train. That name. Madam,
Sir.
learn and train. The name is given different.
1 second. This is. Thank you, sir.
1 second. I will open my presentation.
Yes, sir.
Is my screen visible, madam?
Yes, sir. Yes, sir. Visible,
Yes,
sir.
okay, okay. First of all, I would like to welcome you all who are all gathered over here, and also I would like to thank the organizers of this FDP and management of RMK Engineering College and the coordinators of this program. For all of you, I would like to thank to invite me to share the knowledge in quantum computing, specifically on linear algebra and optimization in the quantum computing. So with this, I would like to start our presentation here. Here we are going to learn about the linear algebra, role of linear algebra in quantum computing. So the objectives of this session is here understand the linear algebra and playing it a major role in quantum computing, and also in the how the quantum representation is done by using the linear algebra in quantum space in the form of vectors and vector spaces and matrices. And also there is, we are using eigenvalues and eigenvectors. So that we will see now. And finally, we will see about the optimization over this quantum computing. Right. So already we know, all of us, the linear algebra is focusing on vectors and vector spaces, matrices, and linear transformations. We will see that what is the role of vectors and vector spaces in quantum computing. So here, this framework is providing in the form of linear equations, whatever the problem statement we are going to solve, that will be transformed into the linear equations in high dimensional spaces. Then we will model that into the geometry transformations like rotations and scaling. And here, this linear algebra can be used in the domain of machine learning, data science, and of physics, and also nowadays we are using in quantum computing. That is the subdomain of physics. And here the content available in the vector is here ordered list of numbers that will represent the magnitude and direction of that specific object. And the vector space can be defined as the set of vectors. So here we will are talking about a single vector. Then when we are having the set of vectors, then that will be coming in the vector space, that will be added together and multiplied by the scalar wherever we required that different calculations. Then matrices, in the sense, already we know it will have the number of columns and rows in the form of rectangular grid. Here we will use the linear functions, data, and transformations. So what is the transformation over here? The transformation, in the sense, we will use some set of functions or single function to map the vectors from one space to another space, that will preserve the operations like addition and multiplications, etc. So these are all the basic mathematics what we have studied in the school days. Now, how can we utilize this linear algebra in quantum computing? As we have seen, the matrices, vectors, and vector space and linear transformations are used by the linear algebra. So here we are going to talk about the quantum computing. In the quantum computing, we will have quantum states and its operations on the quantum states, and we will measure the outcome, that is the output of the quantum states while we are applying these operations. So these are all represented in the form of using linear algebra calculations or representations. So based upon that, here the quantum computing is having qubits. It is called quantum bits, which is represented in the form of vectors, and also there we will use some set of gates like logical gates in the classical computer. So the gates will use the matrix format, and also we will use algorithms. Those algorithms will perform the transformations using the linear equations. So these different representations are useful to efficient modeling of the quantum parallel operations in the quantum computing. So here, when we are, how do we represent the quantum states in vectors? So the qubit will have different states. There is some basic states like 0 and 1. Based upon that, qubit can be modeled in the form of vector representation in complex vector space. Whenever we are having n number of qubits in the system, then it can be described in the form of unit vector, right? The vector will have the magnitude and direction. So based upon that, here that vector will be represented in the 2 power n dimensional space. So that is the thing. So after representing that quantum state in the form of vectors, it will enable the representation of the quantum information, whatever we try to pass into the quantum system. So here, these vectors are enabling the probabilistic computations. It is performing the operations based upon the probabilistic computations, not deterministic. That is very much important property of this quantum state. Where whenever we are measuring the qubit, the quantum state will collapse into either 0 state or 1 state. It will be called here, this representation is called ket 0. Okay, so this is called ket 0. So it will be collapses into ket 0 with the probability of, this is amplitude here alpha square, or the ket 1. This is called ket 1 with the probability of beta square. So here alpha comma beta are the complex numbers in the complex space. That space is called here Hilbert space, that we will see in the forthcoming slides. So this is the fundamental property which is allowing the quantum computers to explore the multi-computational paths. So simultaneously, the parallelism, we have seen that the quantum parallelism is ensured by using the linear transformations that is performing based upon this basic quantum state equations, linear equations. So here, based upon that, we have seen the quantum states can be represented in the form of vectors, right? Then the operations can be represented in the form of matrices, where we are using quantum gates that will perform the operations based upon the input what we are passing using the qubits. So here the quantum gates called rotational gates with respect to the different single qubit states, qubit gates or multi-qubit gates. So here, which is using the unitary matrix, which is representing the quantum state of the qubit. Here, which is providing set of rules, linear algebra is providing set of rules, how the operations can be performed over the qubit by combining and transforming the state from one state to another state to get the expected outcome. Here, the outcome can be measured by using the component is called measurement. The quantum mechanism is having some set of rules, which is using the probability theory and also linear algebra over the Hilbert space. I told you in the previous slide, we will get the number data parameters alpha comma beta in complex space. That complex space is called technically Hilbert space. So the quantum states working on the Hilbert space, this is one of the complex large dimensional space, which is useful to save the, perform the inner products to determine expected output for the given input. So here we will perform the inner products over the say matrices. So matrices are here we are using unitary matrices. So this matrix is based upon the linear algebra operations. Then we will use tensor products here. Already we are familiar with tensor products in deep learning. So which is one of the key in the linear algebra to construct the model on complex multi-qubit systems. That's what I told you. There is two different qubits are there. One is the single qubit and another one is the multiple qubit or multi-qubit. So here the tensor products will be useful. That tensor in the sense that is also one kind of matrix. We can perform by using the powerful processor. There they are using the tensors. So the tensor products will be used to perform the operations on complex multi-qubit systems. And another one important thing is here, the quantum computing is very much faster on the linear algebra equations that is performing on 2 power n dimensional space when we are having the n number of qubits. There is also one of the important property why we are using linear algebra in the quantum computing. Now, one second. Right. So here, what is the difference between the classical and quantum linear algebra? So whenever we are talking about the classical operations, there we will use the bits 0 and 1. So which is processing the data using the linear equations. But in the quantum, which is using the qubits instead of bits, which is utilizing one of the properties called superposition that may represent as 0 and 1 simultaneously. So when we cannot say the specific state either that is 0 or 1. So it will be having 0 and 1. After getting the outcome only, we can come to know what is the state of the qubit. So this can be represented simultaneously. That process is called here, that concept is called superposition over the 2 power n dimensional space. This space is called here Hilbert space. So Hilbert space is useful to preserve the inner product operations. And when we are taking the operations on the matrices, the classical computers are using general matrix operations which are non-reversible. This is one of the important property in quantum computing. That means when we are passing the input to the quantum system, then we will get the output. So from the output, when we are performing some kind of operations, we can get the input state. So from the output, when we are performing some set of operations, we can get the original input, what we pass into the quantum system. So this characteristic is available in the quantum computing. So that's the thing we are giving. So that characteristic is available in the unitary matrices. That unitary matrix is useful in the gate components. Okay, that is the thing. And when you are talking about the computational approach in the classical, which is deterministic and also produces single and a definite result. That means finite result. But in quantum computing, which is following probabilistic based approach, so which can be measured the quantum state by using the probabilistic theory. So it will give any one of the state, and that state can be known at the end of the when we are getting the outcome only. So in between, the states can be varied. And when we are talking about the complexity and the speed, the classical algorithms are very much slow, even for smaller problems. But the quantum system is very faster to the even high dimensional space. That's what Hilbert space with the 2 power n space with, for the n number of qubits. And the principles when we are talking about the classical computing, we are using the Boolean algebra and conventional logic gates. But In quantum, we will use Hilbert space and quantum mechanisms in the form of entanglement. So this is the difference between classical and linear algebra, classical linear algebra and quantum linear algebra. So what are the mathematical components we will use? Already we have seen the vector spaces. It will have sets of vectors. Each vector is representing the quantum states. Here we have seen Ket operation and Ket notation and Bra notation. So here simply we will say in the quantum computing bracket. So this is one of the notation, right? We are using in the quantum computing. So to represent the Ket operations, we will use the column vector. To represent the Bra notation, we will use the row vector. So that's where we are using the linear algebra in the form of vectors. And when we have seen that the Hilbert space is using the representation of inner products, where we will use the scalar value, which is representing the overlap between two quantum states. And the outer product here, we will use the matrix operator, that means the unitary matrix, which is mapping one quantum state to another quantum state. Then we will have another component is called spectral decomposition. This is one of the important component where the given input is decomposes into the eigenvalues and eigenvectors. These eigenvalues and eigenvectors are preserve the quantum states or quantum systems energy, spin, and momentum. So these values will be stored in the form of eigenvalues and eigenvectors, right, in the matrix. Okay, that is the thing. So this is useful to understand how the quantum gates, where there we will see that what are quantum gates available. So the quantum gates, how it will affect the specific state of the quantum qubit, and it will be I mean, example is given here is a quantum phase estimation algorithm for that decomposition. And as I said, we will use the Hilbert space. This is one of the high dimensional space with the complete complex inner product operations. Okay, and the unitary matrix is here, which is one of the operator with characteristic of reversible evolution, and it will preserve the length of the qubit state. So as I said, the reversible is one of the important characteristic in the quantum computing algorithms. And now we will see how we are using the vector spaces of linear algebra and quantum computing. As I said, the qubit will have different states. So here we will have the representation of the qubit here. This is called ket psi. Ket psi. So ket psi equal to alpha times of ket 0 plus beta times of ket 1. So here this is linear equation. Okay. So this is linear equation. So here this is the quantum state. The quantum state is having the is represented in the form of linear equation, right? So here this alpha and beta are complex numbers in the complex space. The state, this is the ket 0 and this one is the ket 1. So that's what represented over here. Quantum states can be represented in the form of vectors. This ket 0 can be represented by using the vector. This ket 1 is also can be represented in the form of vector over the complex Hilbert space. That is the thing. It is allowing superpositions, and also which is having the infinite dimensional, right? These vectors can be represented in the form of ket psi, and due to the vector which is normalized to the unit value, that is here we are representing that square root of this notation, the blue color notation is called Bra notation. Okay, when we are using the angle bracket psi, this symbol, this is called Bra notation. And when we are using pipeline symbol psi, then angle bracket greater than, like this is called angle bracket. So this is called ket notation. This is ket notation. This one is the bra notation. So here the square root of bra psi ket psi equal to 1. That is called we are normalizing the given vector into unit value. And it can be represented in the one-dimensional subspace about the quantum state. And there is some key aspects in the quantum vector representation. The Hilbert space can be represented by using the complex vector space, and it is preserving the inner product of the different quantum states. And as I told you, bracket notation can be represented in the form of vectors. I told you already. So here column vector useful for the ket operation, and the bra is here dual conjugate of the ket. That is the thing. So both are useful to represent the quantum states and probability of the, compute the probabilities. And these are all some of the operations we are using. Superposition can be represented by using this notation: alpha times of ket psi plus beta times of ket pi. Okay, so different values over the complex Hilbert space. And this is a linear equation, and normalization in the sense, as I told you, physical states can be represented in the represented by using the normalized length. And here the basis states are there. What are the components we are using over the quantum states? So the state vector can be expanded in terms of orthonormal basis, and where the coefficients. So here alpha and beta are the coefficients. These are all useful as a amplitude value, probability amplitude of the system. So these are all complex numbers, as I have mentioned in the earlier slides. This can be represented in the form of physical state if the same physical state can be represented in different manner, depends upon the basis state what we are choosing. So here the position can be represented by using the psi, and the momentum can be represented by using the pi notations. That's what given over here. And as I told you, the qubit is represented by using the linear equation, and the qubits are transforming from one state to another state. Okay, that is an important operation over here. So the qubits can be represented by using the Bloch sphere. This diagram showing the Bloch sphere. So here the Bloch sphere is showing the ket 0. This one is the ket 1. So here the top one is a north pole, and the bottom one is the south pole. Okay, so which is having the alpha and beta, two parameters. Both are complex values, and the complex number is having real part and imaginary part. But here we need the real numbers that will be calculated by using the quantum state, which is transforming from one state to another state by using the Bloch sphere. Here the vector is originating at the center of the Bloch sphere. So this is the center of the Bloch sphere. The vector is originated over here and then terminated in this place with respect to this vector. So the center of the space is used for originating the vector, and which is terminating the length based upon the length. I told you the vector is having the magnitude and the direction. So length is the magnitude and this is the direction. All right. So which is terminating at the point which is representing the state of the qubit. So this is origin, and this is the state which is transformed from this state to another state. That is the thing. So it can be visualized by using the Bloch sphere. Qubits can be implemented via two-level quantum system. either electron spin or photon polarization. So that the implementation can be visualized by using the Bloch sphere. And when you are talking about the states in the quantum information, there is two basis states. One is the ket 0. You see here we are using the vector. The vector is 0 can be represented by using the 1, 0, and the ket 1 can be represented 0, 1. Okay, so ket 1 can be represented 0, 1. So these two states are representing the qubit in the ket 0 and ket 1. And what is the Bloch sphere? Why do we need this in the quantum computing? Right. The Madam and sir, if you have any doubt, you can ask me. And if there is any issue, you can tell me immediately. Okay. Here, the Bloch sphere, I told you the Bloch sphere is used to represent the quantum information when it is changing from one state to another state. Why do we use that? The Bloch sphere is representing the geometrical information of a single qubit state, which is mapping the states of the qubit based upon the probability amplitude alpha and beta in 3D unit sphere. So here, as I told you, the north pole, this is the north pole, which is representing ket 0, and the south pole is representing ket 1. Okay, and any point on the surface is called pure superposition state. So you look at that. These are all, our state can be anywhere. Okay, these are all called pure state. Okay, so that's what we are saying. The surface, like, okay, any point on the surface is called pure state on the superposition state, which is defined by angle theta, and this is longitude. Azimuthal angle in the sense longitude, so which is representing by using the pi. So here theta is given polar angle, and pi which is given here with help of longitude value. And we are having different mapping points with respect to the North Pole, South Pole, and equator. So the North Pole is represented by using theta equal to 0. So this is called ground state. So this North Pole is called ground state, right? And the South Pole is called excited state. Right. So here the theta value is 0, right? Here theta value is 180 degree. So we are having different angle 0 to pi. Okay, that is the thing. And when with respect to the equator, here the pi longitude is pi by 2, which is having equal superpositions. When we are having the pi, so this is with respect to the theta. Okay, North Pole and South Pole, which are representing with, which is represented with respect to the theta value, and we are having longitude value. So longitude value here, notation used the pi. So pi equal to 0 in the sense we are getting ket plus. Okay, we are getting ket plus. This is represented over the positive x-axis. This is the ket plus here. Okay, and here ket minus, this one longitude value is 180 degree. This is represented by using the ket minus. Okay, negative x-axis. Likewise, pi equal to pi by 2, which is ket I, or the positive y-axis. This one is ket I. This one is ket minus I. All right. So we can represent the mapping points by using different angles, theta and pi. Here we are having two different states, okay, with respect to the theta and pi. And what are the things, what are the points we have to take away from here? The surface, which is having only pure states, here we will have only pure states, but interior, we will have the mixed states. Okay, here interior, there is the possibility of mixed states. This one is this center origin, that is called maximally mixed state. Okay, and whenever we are having orthogonal quantum states like this, then those points are called antipodal points. These are all important characteristics of the block sphere. The quantum states can be represented, and also the operations will be represented by using the block sphere rotations. Okay, and why do we need this block sphere? As I told you, to visualize the quantum states in 2D complex qubit space on 3D block sphere, we are in need of block sphere representation. The quantum state can be represented by using the ket psi is combination of cos theta by 2 ket 0, cos theta by 2 ket 0 plus e power I phi. This is longitude value, e power I pi sin theta by 2 ket 1. So here, two notations are there, right? So this notation is useful to find the relative phase between the two states, ket 0 and ket 1. The pi is here, as I told you, that is the longitude value. We will use that value to rotate the qubit from one state to another state. That means moving transforming the qubit from one state to another state by rotating that state with respect to pi angle. And here the theta is used to represent the qubit with respect to the ket 0 axis. So here, this is the theta we are using with respect to the jet axis, jet value, right? Here, why we are using the theta by 2? Because here the north pole is 0, south pole is 180 degree. Okay, that is pi. So here we will use the value in this place, right? Based upon the Pythagoras theorem, we will use here that a square plus b square equal to c square. So based upon that, here, when you are using the value into the y, we will use approximately a value theta by 2. So any value, okay, orthogonal, right? Any value to represent that, we will use theta by 2. Pi 180 in the sense 90 degree. So that is the thing. So based upon that, here the notation e power I pi is useful to determine the position of the state on equator. Okay, that is the thing. So here the position of the state is represented by using the e power I pi, this portion of the equation. And as I told you, pi is the longitude. Its range is from 0 to 2 pi. That means 360, right? And which is representing the superposition, which is formed with respect to either in phase or out of the phase angle. That's the thing. So what is the role of this e power I pi? So which is useful to measure the relative phase when global phase is unable to measurable, right? That is the main role playing by the e power I pi. And so till now we have seen what is the linear algebra and role of the linear algebra in quantum computing, and the block sphere representation and the qubit representation. Right? If you have any doubt, you may ask now. Otherwise, we will get into the quantum gates. Okay. So here we are having a single qubit quantum gates and multi-qubit quantum gates. And we will see first quantum gates with respect to the single qubit. The quantum operations can be performed by using the unitary matrices that already we have discussed. These are all useful to preserve the vector length and also maintain the probabilistic nature of the quantum states. So the quantum computer is working based upon the probabilistic approach and which are all stored in the form of matrix or vectors. Here, three fundamental gates we are having to design the quantum circuits to perform the operations. First one is the Pauli X gate. Here, this is also called quantum bit flip gate or quantum NOT gate, right? So, which is represented in the form of this box notation here. We will use the notation by representing the X, and which is equivalent to the classical logic gate, which is performing the NOT operation. So which is equivalent to the NOT gate. So we can simply say the Pauli X gate is equivalent to the logical NOT gate, classical logical NOT gate. Okay, that is the thing. So it swaps the amplitude of ket 0 and ket 1. That means bit flipping. If you pass the input, for example, if you pass the input ket 0, you will get the value ket 1. If you pass the value ket 1 to this Pauli X gate, you will get the output ket 0. So that means we are flipping the bits. So if q bit is 0, we will get the q bit 1. If q bit is 1, we will get the q bit 0. That's why we are saying a bit flip, quantum bit flip gate. Based upon that, here the operations are represented how it is performing. So here the sigma x is representing the matrix of Pauli X gate. The Pauli X gate matrix is given over here. Look at here. So X gate can be represented in the form of matrix 0, 1, 1, 0. Okay. Or is in the form of rows 0, 1, 1, 0. Okay. So this is given over here. Pauli X gate sigma X applying over the state 0. Okay. This is the ket 0, state 0, ket 0. So ket 0 is represented, already we have seen, ket 0 is represented by using the vector, okay, 1, 0. Ket 1 can be represented by using 0, 1. Okay, so this is the representation of the ket 0 and ket 1 of the qubit in the form of vectors. Okay, so now from this notation, you look at here, this one here, we are applying Pauli X gate. Okay, we are applying Pauli X gate on the ket 0. Okay, that is the meaning, right? Applying Pauli X gate on the ket 0. So ket 0 is passing on the Pauli X gate. Then what is the operation? So we are applying X gate, Pauli X gate matrix representation. Then this one is qubit here 0, ket 0 representation. Then we are applying the matrix calculations here 0 and 1. This one plus 1 and 0. Okay, so then we are calculating 1 and 1. So this one and 1 and 0. So that's what given over here. When you're applying this arithmetic calculations, you will get here 0 and 1. So this is equivalent to ket 1. You look at here, this representation is equivalent to ket 1. So when you are applying X gate on the ket 0, Pauli X gate, okay, Pauli X gate operation on the ket 0, your output will become ket 1. Likewise, when you are applying the ket X gate on the ket 1, okay, suppose if you are applying X gate, Pauli X gate on the ket 1, you will apply same kind of operation 0, 1, 1, 0. Then here the Ket1 representation is here 0, 1. Okay, then when you're applying the values, you will get 0 into 0 plus 1 into 1. You will get 1. Okay, 1 into 0 plus 0 into 1, 0. So now you are getting this is equivalent to this representation. So Ket 0. I hope you understand these calculations. So this is the background principle working in the X gate when you are applying input as a Ket 0 or Ket 1. Okay, so it can be represented in the form of generalized format here A, B, okay, the state, any state. Here we are using the Pauli X gate operations. When you're applying that, you will get B over here, A over here. We are swapping. Okay, look at that. Initially, A is in the first position, B is in the second position. Now B becomes in the first position, A becomes in the second position. Okay, so we are saying that bit flip. Okay, quantum bit flip. I hope you understand. So when you want to implement this in Q universe, 1 second, I will open that website. So you can check this, you can implement this in the Q universe platform. So here you can represent your respective operations. Look at here. There is different gates available. There is different gates available. These are all quantum gates, and these are all single qubit gate. Hadamard gate, Pauli X gate, Pauli Y gate, Pauli Z gate, Pauli S dagger, Pauli identity gate. Here T gate, T dagger gate. So these are all single qubit gates, and these are all multi qubit gates. C naught, this one swap gate, CZ controlled Z gate. Then this is controlled Pauli gate, CP, controlled phase gate, and CY gate. So like that we are having, and there is some advanced approaches, QFT, quantum Fourier transformation, and the inverse quantum Fourier transformation. So here, if you want to check your operation, what is our operation over here? You look at that. We are applying the Pauli X gate. So now I am going to add. So I'm taking single qubit. I hope it is visible. Madam, is it visible, madam? Q Universe platform.
Yes, sir, visible.
Okay, madam. Okay, thank you. So here, when you want to test the operations, here we are using the Pauli X gate. So I am using this one, right? Single qubit, so qubit 0. Sorry. For getting the output, we have to use the classical bit. The output will be represented in the form of classical information. So the C0 is called classical bit. So now we are going to check what is the output of this one. So to measure the output, we have to utilize the one of the component is called the measurement. So drag and drop. To the classical bit. That is the representation over here. You look at here. Okay. So first we added the Pauli X gate. Then the output will come. This output to be I want to measure. I want to know the output of this Pauli X gate. For that, I want to use measurement. Measurement in the sense, this is one of the component to measure the outcome of the qubits, what we are using earlier in this place. Okay, so now you see this when you are added, look at that. Always one more thing we should remember, qubit will be having get zero state. So zero state, when you are having the output will become based upon the Pauli X gate, it will be 1. That's what we have seen. Okay, so you see the output can be seen based upon the probability value. When we are passing the qubit is 0, the output will be 1. That is the operation we already have seen in the slide. So output also, you look at here, this is the output. We passed the 0, qubit is 0, we got 1. Suppose if you want to pass qubit 1, we cannot mention 1 over here in the Q0. So what we have to do, we have to make it 1. So now the 1 came. So 1 again passing over here, you look at here. So the first Pauli X gate transforming 0 to 1. Now 1 is the output of the first Pauli gate. Then 1 is passing to second Pauli gate. So now we got the 1. 1 is the qubit. So for 1 qubit, we will get the 0 output. So you look at here, for 1, we are getting 0. I hope you understand this one. Okay. So when you are changing the gates, adding the gates or removing the gates, your code also here, the assembler, which is quantum assembler, so which is writing over here automatically, you can utilize that. So QREG means quantum register, CREG means classical register. Okay, that is the thing. So when you want to add one more qubit, right, you can go to here and you can add over here 2, right? If you want to classical 2 registers means this wires. Look at here, this wire, this is called wire, this line. Each line is called wire. In this platform, which is represented as here, registers. So qubit register 0, qubit register 1, classical register 0, classical register 1. So this is the way to test the single qubit output based upon the Pauli X gate. Okay, that is the thing, right? So next one is here we are having the Pauli Z gate, right? So in this one here, this is another name. Another name is called here phase flip gate. Right, this is called also phase flip gate. This is also single qubit quantum state, which is giving the output with the sign of +1. This is the ket 1. This one is the ket -1. Okay, so actually this can be represented, right? 1 ket 1. Okay, this is the meaning. And this one can be represented -1 ket 1. These values are called amplitudes, coefficient. Okay, coefficient value, or it is called amplitude value. Okay, that is the thing. So here the Z gate having, Z gate can be represented in the form of matrix 1 0 0 -1. Okay, and when you are applying any qubit on the Z gate as a input, right, you will get some output in the form of here Z gate is applied over the ket 0, right? Our output will be ket 0. If you are applying the Z gate on the ket 1, you will get the -1 ket 1. Okay, -1 ket 1, that we can say minus ket 1. Okay, that is the thing. So how can we represent this in the form of linear algebra equations? So here the ket 0 is represented in the form of vector. Already we know, right? Ket 0 means we will have 1 0, right? Ket 1. get 1, we have 0, 1. Okay, that is the thing. So based upon that, here we are applying Pauli jet gate over the get 0. Okay, then when you are performing that matrix operations, 1 into 0, sorry, 1 into 1, 1 plus 0 into 0, 0. Okay, that is the thing. Then we will get 0 into 1, 0 minus 1 into 0, 0. Okay, so we will get 1, 0. That's what we got 1, 0. This 1, 0 is equal to the get 0. That's what the output. Okay, that is the thing. So when you're applying the jet gate up on the get 1, right? So this is the operation jet gate representation, then get 1 representation. Then when you're applying the matrix calculations, you will get minus 1. Okay, this is, you look at here. This is minus 1, minus get 1. Okay, minus get 1. That is the thing. That's what's represented over here. And also, we may apply jet gate on the get plus. So get plus can be represented in the form of vector 1 by root 2, right? 1 by root 2. So actually, it is like this. Right? This is the representation. So when you are taking this operation, this operation, this is the jet gate representation. This is the get plus representation. When you are performing the matrix operations, you are getting get minus. Okay, get minus. Right, that is the thing. So we are flipping the phase. Flipping the phase. Okay, that is the thing. Right. So that means we are flipping that into the 180 degree. Right. That is the meaning of this one. So whenever we want to rotate the or move the transition from 0 degree to 180 degree, then we can go for Pauli jet gate. Right. So that means we should know where can we use the Pauli jet gate, where can we use the Pauli X gate, where can we use the Pauli Y gate, where can we use the T gate, where can we use the T tagger. So like that, we should know the basic background working principle of this different gates to utilize in our circuits. So to check this operation in the Q universe, you can go to the universe platform here and you can check it here. Okay, so to remove these lines, again you have to go for manage, because I am using only single qubit, so I am using single lines. Okay, so I don't want this Pauli X gate, so I am removing that and I'm freshly starting. So now you look at that, I want to use jet gate, Pauli jet gate. Then I want to measure what is the output for measuring measurement component. Look at that. When you are passing 0, okay, when you are passing 0 for the Pauli jet gate, so you are getting 0. So if you want to continuously check with the different values, okay, different values, you can check it out by using different number of gates by adding over here. Okay, that is the thing. So now 0, then 1. Now, if you add a NOT gate over here, that means Pauli X gate, 0 passing to X gate, then you are getting 1 as the output. So now we got 1. So like this, we can test our different gate output values based upon the different requirement. Okay. Then another one is Pauli Y gate, so which is called combined bit flip. The Pauli Y gate, again, this is also single qubit, which is combining two things. One is Pauli X and another one is Pauli jet. So Pauli X already we know that is the NOT gate, that means the bit flipping 0 to 1, 1 to 0. And jet gate is phase flip, that means 0 to 180 degree. Okay, that is the thing. So if you want to use both operations together, okay, if you want to use both operations together, then we can select Pauli Y gate. simply it is called Y gate. Okay, so this can be represented in the matrix 0 minus I 0. Okay, so this is the matrix representation of the Pauli Y gate. Okay, as we have seen, it can be rotated with 180 degree. Okay, with respect to the y-axis. So previously, this is rotated with respect to z-axis. This is rotated with respect to the x-axis. So like that, y-gate is rotated with respect to the y-axis. Okay, that's the thing. So based upon the principle, when you are having y-gate like this, when you are passing input get 0, then output will be, right, I get 1. Likewise, when you are passing get 1, input is, okay, we can say like this. Your input is get 1. Then your output will be minus I get 0. You look at that here, a bit is also flipped, right? For 0, we got 1. That is the bit flipping. Then here there is no phase. Here we are as adding I. Okay, and here 1. Here we got 0, and here we got minus I. So bit flipping and phase flipping. So both are applicable when you are replacing the Pauli Y gate. So here the Pauli Y gate values are given over here. Okay, this is the value of I. This is the value of here minus I get 0. This is I get. Okay, that is the thing, right? So if you want to test this one, you can test it in the QUniverse platform by using this adding the Y gate over the Q bit 0, right? And likewise, there is another one gate that is called Hadamard gate, so which is also called superposition creator. So that means the qubit may be in 0 state and also get 1 state. Okay, so equal probability 50-50. So 50% of being state 0, 50% of being in the state 1. So we cannot determine the state of the qubit either which is in the 0 or 1. There is the possibility 50% of probability being in the state 0, 50% of probability of being in the state 1. Okay, so when you are applying this get 0 on the Hadamard gate, which is creating get 0 plus get 1 divided by square root 2. So that means this is the value of the get plus. That means when you are passing get 0, this is the Hadamard gate. Okay, this is the Hadamard gate. So, yes, madam. Okay. When you are having the Hadamard gate, so get 0 is the input, then your output will be here get plus. Okay, the get plus is equivalent to this value. Okay, likewise, when you are passing get 1, then your output will be get minus. Okay, so its value is equivalent to here get 0 minus get 1, this value by square root 2. Okay, that is the thing. So here, if you are using continuously, two Hadamard gates like this, you look at that. If you are using 2 Hadamard gates continuously, you will get the value identity matrix. Okay, like 1, 0, 0, 1. You'll get the identity matrix. That's what this point. When you are using 2 Hadamard gates, that means square of the Hadamard gate will provide the value identity gate, this matrix transition. Okay, And when you're applying the Hadamard gate to the same qubit twice, there will be no effect. Okay, that is the thing. So based upon that, you can test your output in the Q universe here by adding, right? I will delete this. Hadamard gate. Okay, look at that, which is having what we have seen equal superposition. Look at that superposition creator. Okay, superposition creator. That what I told you, 50% of probability being in output 0, 50% of probability being in gate 1. So that means it may be in the 0 state or it may be in the 1 state. Okay, right? It is probability value. So 50-50. So that's what which is saying output. You look at here. When you're adding the Hadamard here measuring, when you're measuring, you look at that 50% of state 0. Okay, 50% of state 0, probability of 50% of state being 1. Our input is here 0, F0, Hadamard gate. When you're adding one more Hadamard gate, look at it. When you're adding one more Hadamard gate, the 100% of probability get 0. That means our input is also 0, output is also 0. Look at here, state 0. That's what we are saying. You see, once again, I'm repeating. Input is 0. Again, output also we are getting 0. 100% probability. That's what we have seen this point. The last point here. Here this last point, applying Hadamard gate to the same qubit twice. Okay, same qubit twice has no effect on it. That's what. Same, we are getting same input. I mean output as a 0. Okay, input also 0, output also 0. That means there is no effect on it. So that's what we are saying. So no need to add sequentially Hadamard gate one after another in the same qubit. Okay, that's what given over here. I hope you understand. Okay, right. So this is about the Hadamard gate, and still we are having different single qubit gates. We have seen X gate, Y gate, Z gate, and Hadamard gate. Still we are having S gate, which is represented by using the matrix 1, 0, 0, I. Then S dagger. S dagger gate is also represented 1, 0, 0 minus I. This is T gate. Again, rotations also given with respect to this z-axis, right? Minus pi by 2. That means minus 90 degree. Here pi by 4. Okay, 45 degree with respect to z-axis. That is longitude. Okay, and minus pi by 4, minus 45 degree with respect to z-axis. So here each gate is represented by using some matrix representation. So here T is having the matrix of quantum information, that state information is represented 1, 0, 0 e power I pi by 4. Okay, pi by 4 is here 45 degree, and this is angle pi. Angle pi. This means longitude. Azimuthal angle. Okay. T dagger 1, 0, 0 e power minus I pi by 4. So here this can be represented in the form of 1, 0, 0, 1 minus I by root 2. Okay, so these are all the different single qubit gates we can use to design our quantum circuit to get the expected outcome for our problem statement. Okay, that is the thing. And 1 minute. So now, till now, we have seen a single qubit state. That means in the Q universe, we have seen Q0. That is a single qubit state. Okay, now when we want to design the system with the multi-qubit, then we have to go for a different kind of gates. Okay, so whenever you want to design the multi-qubit systems, we will have minimum 2 qubits or more number of qubits to design the single system. Okay, and which is enabling the exponential computational capacity compared to the classical bits. That's what already we have seen, which is very faster than the classical systems. And the state can be represented here in the 2 power n dimensional space. Look at here. We can represent it in the form of kit psi, right? Here, product of kit pi. So this is called, right, inner product. Okay, it can be represented by using the inner product. So each quantum state can be represented by using the vector. Then we will apply the tensor products over this one. Okay, the operations are performed using the unitary gates. Here, we will example I have given C NOT gate, that is controlled NOT gate, which is which is performing the operations on the multi-qubit space. The C NOT gate is having 4 basis states. One is kit 00, kit 01, kit 10, and kit 11. So here, the C NOT gate is using one of the operation is called entanglement that we will see elaborately in the forthcoming slide, which is one of the feature on the multi-qubit system, which is intertwining the different qubits to perform the operation. And here, single qubit is influencing on another qubit to build the quantum circuit and performing the entanglement operations. Here, the unitary operations are performing on n number of qubits with representation of 2 power n by 2 power n matrix. 2 power n is the high-dimensional data space, complex Hilbert space. Okay, so this can be local or global. Okay, that is the thing. So based upon that, we will see what is the entanglement in quantum computing. Entanglement in the sense, this is with respect to the physics domain. The quantum entanglement in the sense where 2 or more particles will be linked together to perform the operation by checking the state of one particle, determining the state of another particle. That means if you take this is one of the state, then which is determining the output of this one, state of another particle. Okay, that is the meaning. Okay, even though they may be separated with large distance with respect to the physics domain. Okay, particles. Likewise, in qubits. Okay, in qubits, which is representing the quantum correlation between different qubits which perform the operation based upon the representing the states to be interdependent. Okay, interdependent. Okay, so here, what is the meaning of interdependent? This is one bit. This is another bit. This output of this operation, output of this bit is depends upon this bit. Okay, output of the second bit is depends upon the previous bit. So this bit is depending on previous one. That's what we are saying. It is allowing the states to be interdependent, even though it is separated. That may be small distance or large distance. Okay, so which is one of the powerful and unique feature in the quantum computing, which is distinguishes the quantum computer from classical machines, and also which is providing the entangled state. Entangled state in the sense which is one of the multi-qubit state. Okay, it is important multi-qubit states, not a single qubit state. That is entangled state in which individual qubits do not have independent values because uh, qubit states are interdependent on each other. Okay, that's what we are saying. So here, instead of that, states are linked or connected that measures one qubit instantly revealing the information about another qubit. Okay, one qubit, this qubit revealing the output of the another qubit. That is the thing. For example, Bell states. Okay, we will see that. So these are the different Bell states we are having over quantum computing. So these Bell states are represented by using the two qubits, right? First qubit, second qubit. Okay, two qubits. It takes on a specific value. The second qubit is forced to take on the specific value, right? Here, the one of the two qubits is measured. That means if you measure first qubit, which is influencing another qubit's output, that is the meaning of the second point. Okay, the output of this qubit influencing by the first qubit. Okay, that is the thing. So here you see we are having different qubits. Okay, this is pi plus 0, 0. This is 1, 0. This is 0, 1. This is sorry. This is 1, 1. This is 1, 0. Okay, right. So when you are checking the when you are applying this, the first qubit here, the first qubit, this is called control qubit, and the second qubit, this one Q1, this is the target qubit. So what will happen in this one? Okay, so here the first qubit is represented by using dot. Okay, control bit is represented by using the dot, and the target bit is target qubit is represented by using the circled encircled plus, right? And the connection between two qubits is by given by using the vertical line, right? So here you look at that in the one of the example is here. Oh, one second. So this here, this is given in the form of Bell state. The first qubit is influencing second qubit. Okay, so these are all the given representation. We will check in the Q-universe. So we are talking about now two qubits. Am I right? Multi-qubit. So I am removing this. I want to add one more qubit. Okay. Right. I added one more qubit. Now I will use that output circuit to represent this. Hadamard gate. Yes, I added Hadam. I'm adding Hadamard gate here. Qubit 0. Then here I'm going to add CNOT gate. Okay, CNOT gate. Now you see the output. Look at here. As I told you, we are having the Bell state. Bell state here. Look at that. Two qubits. Two qubits means four combinations: 0, 0, 0, 1, 1, 1, 1, 0. You look at here. Okay. So 0, 0 plus 1, 1. I hope you understand this one. Okay. So when you're applying 0, 0, okay, our input is 2 qubits. Our input is 2 qubits. 2, 0 is also 0. Here, look at here. The left side pi plus 0, 0. I wrote in the green color font pi 0, 0. Pi is the quantum state. 0, 0 is the input. Q0 is also 0. First qubit Q0, second qubit Q1 is also 0. Right? Now, we are applying the Hadamard gate. Then this is the multi-qubit system. So, which is connecting C0 gate. So, the dot is representing the first qubit and the plus is representing the second. I mean, they both together. This is target gate, control bit, target bit, qubit. Okay. So, now output you see, actually we got 0, 0, right? 1, 1. You look at here. Output is here 0, 0, 50%, 1, 1. Okay, that is the thing, right? So like that, when you want to pass here 1, 0, okay, Q0 is 1, right? That's why we are applying the NOT gate over here. When you are applying NOT gate over here, we'll move a little bit. Now your output you see right. You will get the values here as the output. So likewise, you can test all the inputs. Okay, that is the thing. So these are all 4 different build states over here. You can test in the QUniverse platform to know the output, how we are getting. So based upon that, I will complete 1 second, 1 second. Here, the entangler, you look at that as per the diagram I have shown and also the experiment, we can use the C0 gate. C0 gate means this one. This is the C0 gate, multi-qubit. This is the Q0, this is Q1, this is control bit, and this one is the target bit. So it can be represented in the form of matrix. Since we are having 4 different states, and input when you are passing 0, 0. So first qubit is the control bit, second qubit is the target bit. So 0 will not disturb. 0, 0 means output, again output will be 0, 0. This is control bit, this is target bit. Okay. 0, 1 means 0 will not change anything. Again output will be 0, 1. 1, 0 means if a control bit is 1, the bit will be flipped. 1, 1 you will get. Then control bit is 1, here 1, this bit will be flipped. 1, 0 you will get. That's what given over here, right? As I told you, C0 gate is used following the quantum principle. You can get the reversibility, and which is useful for the entangling to create the build states that we have seen in the previous experiment. And if you want to use continuously different gates, then you can create another gate. All right. So that is the thing. So for that also you can use the C0 gate operation. So with this, I will conclude now. We will meet in the next session at 11 o'clock. Thank you.
Thank you, sir, for your highly informative and insightful session on quantum linear algebra and optimization. Your valuable presentation has given us a deeper understanding of the emerging concepts in quantum computing, optimization techniques, and their real world applications, sir. On behalf of our organization team and all the participants, I extend our heartfelt gratitude to Dr. Kupuswamy for delivering such a wonderful session. Thank you once again, sir.
Thank you, madam. Thank you.
We also
I will,
thank all the participants of your for your active presence and participation. And our attendance and feedback link is posted in the chat box. So kindly complete it immediately. And let's now go for a tea break. And all are requested to join back at 11 a.m. For the next session on variational quantum algorithms for machine learning.
thank you, madam. Thank you.
Thank you, sir. Thank you, participants. Join at 11 a.m. sharp. One more information, participants are requested to join the session using your name only. So your clear name should be mentioned so that it will be helpful for our attendance monitoring purpose. And also the participants are requested to fill the attendance and feedback form for every session. It is mandatory. Welcome back, participants. Once again, we welcome you all for the next session on variational quantum algorithms for machine learning. Now, I request Dr. Kuppusamy sir to take over the session and share his valuable insights. Please, sir.
Yeah, madam, good morning. Madam, is my slides visible?
Yes, sir. Yes, sir.
Okay,
Visible,
okay.
sir. You may
Okay,
proceed.
madam.
Thank you, sir.
Yeah. Yeah, once again, good morning to all of you gathered over here. In the previous session, we have seen different type of gates in the quantum computing. And when we want to solve the problems in quantum circuit, I mean quantum computing, we may use quantum circuits for some kind of problem statements. Okay, so there we will use quantum algorithms, and also that algorithms will be useful to design the quantum circuits with the help of quantum gates to solve our problem statements. So here we will see some of the variational quantum algorithms. Um, second. Okay, the variational quantum algorithms using in the quantum computing, which are all hybrid form, combination of classical algorithms and also um, quantum algorithms. Which is running or executing in the noisy intermediate scale quantum. Simply, it is called NISQ devices. By combining small quantum circuits with the classical optimization. That means we know already, if you have studied neural networks, in that neural networks, we are having the optimization by using the gradient descent algorithms. So same kind of approaches we will use over here to optimize our algorithm to get the better solution. That is the thing. So here to optimize the variational quantum circuits, we will use the optimization approaches that minimizing the error. Error means already we know total error, that is called cost. Cost, or we can say total error in the neural network, normal neural network. But here in the quantum circuits, we will say that is the cost. So we have to reduce the total error over the quantum circuits, or what is the output we are getting. So by improve the performance of our model or quantum circuits to provide a better solution. That is the thing. So here the quantum circuits can be called variational quantum circuits and also parameterized quantum circuits. Both are same. Okay. What are the components available in the variational quantum algorithms? Right, that we will see now. Here, the parameterized quantum circuits, also called ansatz. We will see what is ansatz later. The circuit is designed with gates, quantum gates, which are all adjustable. That means we will have the gates which are having the matrix representation that will be applied over the inputs. Then it will transition from one state to another state to get the expected solutions. There we will use angles, that is called theta, right? The cost function which is used to calculate the uh, uh, quantum output in the form of ground state energy, right? And we will use classical optimizers like Adam, stochastic gradient descent, root mean square error, like that. We can use the classical optimizers to update the parameters which are useful to design the quantum circuits. Okay, that is the thing. We have to repeat that process until we are getting the better solution or optimal solution. That is called converging point in the neural network. So until reaching the convergence, we will keep on iterate the process till we are getting optimal solution. Okay, there is a different variational quantum algorithms, right? One is the variational quantum eigensolver, which is useful to find the ground state energy of a Hamiltonian. I will say what is Hamiltonian later. Okay, which is essential for quantum chemistry simulations or in the form of quantum materials like that. And another algorithm is here quantum approximation optimization algorithm, which is useful to solve the combinatorial optimization problems. And also another algorithm is here QNN, which is useful for classification. So these are all different variational quantum algorithms, right? What is ansatz in the quantum computing, right? Ansatz is having here available in the VQC, that means variational quantum circuit, which is the starting point to solve the problem, which is act as a trivial wave function. It is trivial, not a trial. A trivial wave function in variational algorithms. That means we will use the wave function over here to solve the problem in the quantum computing. For example, we can say variational quantum eigensolver and also quantum neural network and quantum approximation optimization algorithms, all those things, in which the circuit parameters, that is the rotation angles, are fine-tuned hyperparameter, like a hyperparameters. Okay, we will tune this parameters to find the optimal solution. So from this, we have to define what is the ansatz. Ansatz is defined as the arrangement of quantum gates. You look at here, this is one of the ansatz. Here, quantum gates, Y gate, Pauli Y gate is arranged. You look at here, we are having three qubit structure. In this 3-qubit structure, the Y gate is arranged over here, which is using the angles to rotate from one state to another state. I mean, to move from one state to another state. That's why it is represented by using the R. R in the sense rotational. Okay. Then we are using some entanglements over here. Here also we are using some entanglements. Then this is another layer of Y gates which are arranged over here. So from this, we can say the arrangement of quantum gates and qubits in the form of different layers tailored to the problem's physical properties. That means whatever the number of layers you want, you can add. Here we have added 3 layers. If you want to add 5 layers or 7 layers or 8 layers like that, you can keep on add the number of layers. So you can arrange the number of layers with the help of quantum gates is called ansatz. Okay, the good ansatz balances the capacity of representing complex states. That is called we are expressing our problem statement in the form of complex states with the ability to optimize its parameters. Here we will have each gate. Here each gate is having its own angle, theta. So this is the parameter here we have to optimize. That means fine tune to get the optimal solution. So that will be done during the training process. Okay, that's the thing we are saying, trainability. Right. So the variational optimization is another step. Here we will keep on update the parameters theta using the iterative process with help of classical optimizers like adaptive moment estimator. Okay. So based upon this classical optimizer, we can keep on update the rotation angles. Those are all tunable parameters until the circuit is providing you the best solution at some converging point. Okay, so these are all important steps in the variational quantum circuits. So in the quantum variational circuits, okay, first we will see which is equivalent to the neural network. That is here in quantum computing, I have taken as a quantum neural network. So here, how can we use the quantum variational circuit in the variational quantum algorithm? We will take classical data that should be transformed into the quantum information. Okay, so for that we will use the quantum encoding. Then after encoding that information into the quantum states, then we will use the quantum circuit to receive the input in the form of quantum states. Then we will do some process by using the variational quantum circuits. This is the variational quantum circuits here, right? Then the output of this quantum circuit will be measured by using the measurement component. The measurement component provide the output. That output should be compared with the expected output. I mean original output. Then we will calculate the cost over here. If cost is more, that means total error is more, then we have to go for back propagation. That is the parameter updation that is coming in the concept of optimization. Okay, so that we will see over here step by step. First, classical data. So whenever we are taking the information, then classical data should be transforming into the quantum information. Then we have to apply the quantum embedding. Okay, that is the thing. So classical information may be in the form of either image data or sensor data. Sensor data may be raw data that should be again apply the pre-processing approach. Then we have to transform into whatever the format you want in the text data, alphanumerical or whatever it is. Then financial data set, and this data should be mapped into the quantum state. So this is the classical data. We have to transform that into the quantum states. Okay. So the quantum embedding is data embedding is one of the process here. The classical data is transforming into the quantum states. Already we know the quantum state can be represented in the form of ket psi, okay, ket psi equal to alpha times of ket 0 plus beta times of ket 1. This is linear equation. You see, we are using the linear algebra over here, right? Then ket 0 can be represented by using the vector, that is linear algebra. The ket 1 can be represented by using the vector, right? That is the thing. And to transform this classical data into quantum states, we have to use encoding methods. There we are having different encoding methods. One is the basis encoding, angle encoding. Third option is amplitude encoding. Another one is feature maps. Here, most of the times we will use angle encoding method as per the literature what I have gone through, right? So based upon the angle encoding method, the given data is transforming into the quantum states, right? The encoding is determining the how we are expressing the quantum, given data in the form of quantum information, and which is expressing the, determining the performance of the quantum variational circuit based upon our expected output, and we have to determine the hardware feasibility, because quantum in the sense mostly they are depending upon the hardwares, quantum computing hardware. Okay, but before getting into the hardware, we can do the same process in quantum simulator. Okay, so first we have to do the execution in quantum simulator. After, if you are satisfied with the quantum simulation results, then same code can be applied into the quantum hardware. Right, that is the thing. So we have to determine the hardware feasibility to our data. Right, that is the thing. So after that, here quantum feature space is used to represent our quantum state in the Hilbert space. Already we have seen Hilbert space is one of the complex n-dimensional, 2 power n-dimensional space. There, quantum information can be projected. Okay, so the dimension can grow exponentially with any number of qubits. If you have n number of qubits, then your space will grow till 2 power n dimensional space. Okay, that is the thing. So which is enabling complex pattern representation. That's what, because the space itself complete complex space. So the data can be represented in the form of complex pattern, and which is having high dimensional feature mapping, which is almost similar to the kernel trick we are using in the classical machine learning techniques like SVM, RBF network, so like that. Okay, so which is almost similar to the kernel trick, right? And now we are coming into the variational quantum circuits, that which is using the variational quantum algorithms here. This is also called parameterized quantum circuit, PQC. Okay, that is the thing. Now, what are the components available in the variational quantum circuits? That's what we have to update the knowledge before designing the quantum circuit. So it will have quantum gates. Okay, any kind of quantum gates. So this you have to select based upon your problem statement. Okay, based upon your problem statement, you have to design, you have to select what kind of quantum gates are needed. Already I told you we are having single qubit quantum state, quantum gates, and also multiple state quantum gates. Okay, so you have to select what kind of quantum gates are needed based upon your problem statement. Then, based upon that, we will have the number of parameters, rotational gate parameters. Those are all trainable parameters. It will change. Okay, trainable in the sense it will be updatable by using the parameter shift ruling. Okay, parameter shift rule is there. During the training, these parameters can be updated by using this algorithm. So it acts as a quantum model, like a neural network in the typical artificial neural network. So which are all having the different layers, data encoding gates. That's what given over here. You see, this is the quantum embedding state. Here we will use encoding methods, data encoding gates. Mostly we will use Hadamard gates, okay, or sometimes we will use rotational Y gates, okay. That means Pauli Y gates with rotational angle, and that's what given over here. You see trainable rotational gates and entangling gates. Okay, so here based upon the structure, you see we are initializing. Uh, uh, First, we will select how many qubits are needed. Okay, so you assume that I am selecting 3 qubits. Okay, 3 qubits. So 3 qubits can be represented. One is Q0, another one is Q1, and the second one is, third one is Q2. So now all the qubits are initialized as 0. Okay, state get 0. Okay, all will be initialized as 0. Right. Then here we are initializing with some gates. Okay, here we are giving some gates. So before that, here we have to use the embedding method, encoding methods, quantum embedding. Okay, that is the thing. We can use any kind of gates to represent the quantum information, right? That's what this one. Then we will represent, we can construct the variational quantum circuit here. Okay, so here Hadamard gate we are using. In the Q2 we are using Pauli X gate, right? And here we are using entanglement between Q0 and Q1, right? Then here we are applying rotation. So until here, you look at that. Until here, we are applying some number of gates. That may be a single qubit gate, that may be a multi-qubit gates. So entirely together, it is called, right, variational circuit. This is variational circuit. Okay, so here you can add any number of gates. What we have seen in the previous session, right? If you want to bit flip, then you go for X gate. If you want to phase shift, then you can go for Z gate. Okay, if you want superposition, you can go for Hadamard gate. So like that, you should first define your requirement. Okay, based upon your requirement, you can add the gate with the respective qubit wire. So this line is called wire. Okay, Q0 is one wire, Q1 is another wire, Q2 is another wire. So 3 qubits, 3 wires are there. So you can select any number of gates. Okay, that is the thing. So this is given in the single slide, that same diagram. Now, as per the steps given in the variational quantum circuit, first each qubit should be initialized by using the linear algebra representation, vector representation. There we have used 3 qubits, Q0, Q1, Q2. Okay, all 3 qubits initialized as 0. That's what we have represented over here. All are initialized as 0. Okay, then superposition. If you want to add superposition to the qubit, go for that means select the Hadamard gate. That's what given over here. If you want to flip the bits, then you go for Pauli X gate. That's what we have seen. And if you want to connect or interconnect 2 qubits, go for C0 gate. Right? That technical process is called entanglement. That's what you look at here. If you want to interconnect 2 different qubits, then go for entanglement. So you can go for entanglement like this also. Here on entanglement, here on entanglement. Look at here. Connecting 3 qubits. This is also possible. Okay, so you can go for right entanglement process if you want, right? Which is conditional. That means if qubit 0 state is equal to 1, that means what I said already in the previous session. If first qubit is control bit, second qubit is here target bit. If this is 0, nothing will be changed. If this is 1, then this qubit, second qubit will be flipped. Okay, that's what given over here. This diagram is showing that initially, right, 2 qubits we are selecting. Okay, so both are in the ket 0, 0, both are in the ket 0, north pole. Both are in the north pole, ket 0. Then here we are applying the entanglement connection. Here applied. Okay, then based upon that, here we are saying this is intermediate state. That is the association between two qubits. Association between two qubits wherever it is available. It may be at any distance, small distance or large distance. Then based upon this, based upon the control bit, okay, based upon the control bit, the target bit is changing. Okay, that's what which is represented over here. You look at that, the position is right showing over here by the direction is changed for the control bit. I mean a target bit. Okay, that is what given over here. So one bit, one qubit is influencing the output of another qubit. That's what given over here. And if you want to use rotation, then go for phase gate. Okay, which is rotating around the jet axis. Here we are having when you're taking the block sphere, we are having three different axes. Okay, here jet axis, sorry, this is jet axis. Here, then you can take y and ex. Sometimes you may have like this also. This is jet axis. This is ex. This one is y. Like that also sometimes you may have seen. So this is ket 0. This one is I. This one is plus. Okay, so like that you can have different representation in different materials. Okay, and finally here finally we will have measurement. So here the qubit quantum states are calculated based upon the VQC. Then this output should be measured. Okay, output should be measured. For measuring that output, we will use a measurement component. Again, this measurement component you can use for each qubit. Okay, for each qubit, and this should be connected. This should be converted into the classical bits. Output should be in the classical form. Okay, typical classical form. Okay, so for that we will use classical lines. Okay, so here you see here we will have C1, C2. If you want output in the three lines, then we will add three lines here. Okay, classical bits. This outputs will be joined over here. Okay, that is the thing. So whatever the number of classical bits needed in the output, we can add those one. That's what we are saying here. Measuring a qubit makes it collapse onto the defined state. Okay, defined state. That state is called here eigenstate. Eigenstate is having eigenvalues and eigenvectors. So eigenvectors and eigenvalues will have the values of the qubits energy, spin, okay, and momentum. Okay, these values will be available in the eigenstates. Okay, this value, the measured value reflects this state. Okay, that's the thing. So in the measurement, the quantum state is converted into the classical output. Already we have seen in the QNUS platform, right, in the form of bar chart. Okay, so here my input is quantum state 0, 506 times, totally 1000 times we are taking. In that probability, here 506 times we are getting 0, 494 times we are getting 1. Okay, that is the thing. These values are predicted. After that, we have to apply the loss function to calculate the cost. That means cost function. We have to apply the cost function to calculate the total error. Right. So based upon that, here we are in the position this step. Okay, first we have initialized, then execute the quantum circuit, that is VQC, then measure the output. Now we are in the calculation of the total loss. Okay, so total loss can be calculated here somewhere. So, yeah. So this is the cost function, total loss. Here we have to calculate the difference between our output calculated from the network. Network means VQC and our required output, target output. Which is calculating the difference between the network output and the target output. The formula is given over here, based upon the cost function, right? C equal to 1 by N, right? N is here the number of training samples. Then summation of X equal to 1 to N number of samples. Here pi out. Pi out is here. We are using bra notation. You got here. This is the bra notation, row vector. Then this is row out, which is the output, right? Which is the output calculated here. And this one is the ket notation. Okay, ket notation, which is the column vector. Okay, that is the thing. So based upon this, we will get output total error from the target between difference between the target output and the predicted output. Right. So here you can fix some threshold value. The cost, if it is more than some threshold value, then you have to go for next iteration. Okay. Otherwise, you can stop the process. That is the thing. Based upon that, here, if you go for next iteration, already you see. Here, okay, in this VQC, you have some angles, theta. Okay, theta value here, theta value here, right? Theta value here. Okay, based upon this, you assume that theta equal to 0.7, here theta equal to 0.3, theta equal to 0.9. So you got some output over here. Okay, you got some output over here. You assume that you got total error 50%. 50% error, but we can allow 25% error. So 50% is greater than 25%. So I want to go for next iteration. Okay, now I have to update this parameter values. These parameter values I want to change, update. So for that, here we can use parameter updation algorithm, right? By using any one of the optimization approach, either gradient descent, batch gradient descent, or ADAM, or simultaneous perturbation, stochastic approximation. So like that, you can use any one of the optimizer to update the parameter values. Okay, so for that, we can use process. That process is called parameter shift rule. Parameter shift rule. So this algorithm is useful to update the parameter values. So when you are updating the parameter values, here new values will come. Here it may be 0.299, it may be 0.71, right? It may be 0.899. So like that, parameters will be updated. Again, we have to go for second iteration. Okay, again you have to process the same input values, but different parameter updated parameter values. You will get output at second iteration. So now again you will calculate the error. You assume that 48% you are getting error, but which is again greater than the 25%. Again go for third iteration. Okay, so like that, we have to keep on do that until we are converging towards the end, converging towards the error or cost close to the 0 or your 25%. We got 25% threshold. So you have to go towards the 25%. So this is what the optimization process, we have to keep on do that in this variational quantum circuit. I hope you understood this. So here, this is representing here you look at that. I am comparing. This is classical neural network. Okay, there we will use the bits and activation functions like sigmoid, softmax, uh, tan-H activation function, or tan-H, softmax, sigmoid, and also relu, leaky relu. So like that, we can use any activation function in the classical approach. But here there is no superposition and no entanglement. At the same time, when you are using the variational quantum algorithms, here we are having qubits instead of classical bits. And also we are having quantum gates instead of activation functions. And we are having superposition. There is no superposition here. And here we are having entanglement. No entanglement in the typical neural network. So this is the major difference. Based upon that, here I have given, you look at here, this is the network we are using here. This is unitary matrix with respect to the input. We are applying the data encoding. Already I told you there is different encoding method like angle encoding, amplitude encoding methods, and feature map methods, and basic encoding. Four different types of that. We can apply any one of the encoding method. So that's what this is, the typical neural network here, which is learning the pattern. Like that, this data encoding is transforming the information into quantum states. Then after that, here we are applying the rotational gates with respect to the angles. Rotational gates with respect to the angles. So here, which is moving the quantum state from one state to another state to identify the expected solution, right? Then we are calculating the output by using the measurement components. Then we are calculating the cost. Okay, cost is calculated, right? We are checking if your threshold is 25% of error is allowed, means we are calculating the total error. Total error, if it is 25%, then we can stop. If it is greater than 25%, then we have to go for back propagation, that is called parameter operation. Okay, that's what I are showing here. And this is explaining how that features are encoding. Okay, transforming the classical data into the quantum state. Ansatz are having combination of different gates, which is applying the trainable rotations and entangling operations, what we have discussed already. And this circuit is reversible, and also non-linearity is also appearing, because we are using the measurement and combination of classical optimization. And this expected values decoded into classical outputs in the measurement component. Okay, same thing which is explained over here step by step. Okay, that's the thing. Now we will see the parameters updation, the theta. Okay, how that theta is updated by using the optimization approach. Here we will use the gradient descent optimization approach, gradient based optimization, right? This is the error what we have calculated. And here the direct back propagation is not possible like in the typical classical method. So we have to go for parameter shift rule. Okay, this parameter shift rule is computing the derivations. The derivation means partial derivation. Dou C cost with respect to the parameter theta here. Okay, so we will use parameter shift rule, which is shifting the circuit parameters plus or minus pi by 2. That is theta by 2. Theta is here, range is from 0 to pi. Okay, 0 to pi. That's why we are using pi by 2. Okay. The optimizer, which is updating the parameters, here you can use either stochastic gradient descent or Adam optimizer. So this is the generalized formula. Okay. At the time step t, we have the old value. What we are using in the what you call the normal neural network. This is the formula W new equal to W old minus alpha times of dou J divided by dou W. Okay, this is the formula. Same kind of formula here we are applying. You look at here. Theta. Theta is the parameter, old parameter. This is the new parameter. Time step additionally next time step. This is old time step or current time step. This can be said current time step. This is the next time step. Okay, we are calculating. Minus alpha is the learning parameter. Then delta is this. We are applying the derivations, or the J is here cost. Here we are using the C. J is calculated by using the with respect to the W. Here we are using the theta. That's it. It's almost similar to the typical neural network optimization. So here we are using the quantum neural network optimization by using the classical optimization approaches. Okay. And applications here, we can go for molecular simulation, drug discovery, medical imaging. There we can use the quantum CNN, financial forecasting. There also we can use quantum neural networks and cyber security and cryptography. Okay, this is about the quantum neural networks. And one more algorithm I have prepared in the various quantum algorithms, that is quantum approximation algorithm. Just I will take in 10 minutes. Second. Yeah. Actually, this is the topic we have to discuss in the first session itself. So quantum optimization in the sense here, which is utilizing the quantum computing principles, superposition, entanglement, and interference to find out the best solution. Okay, that is the optimization, obviously. So here, which is identifying the global minimum. Already we know when you are taking the loss curve, okay, here you will have number of iterations. Okay, number of iterations. When you are having number of iterations, you may have the loss should be reduced. That loss means here cost, total error. Total error should be reduced here, like this it will come. Okay, so when you're taking this curve here, this is the point. This is one of the point. There is the possibility. Okay, you see error is here. You assume that 0, then 0.5, then 1, then 1.5, then 2, 3, like this. Okay, look at that. This is the point 1.5. Again, error is increasing over here. 1.6, 1.8, like that. It became almost 1.9. So what our algorithm will think, this is the minimum point. This is the minimum error. After this, error is increasing. So it assumes that this is the minimum error. So it is called a local minimum. So it is one of the minimum. And again, you look at that here, you got 1. This is another minimum. Here it is 0.5. This is another minimum. Minimum 3, minimum 2, minimum 1. So these are all called local minimum. Okay, again, you look at that. Here we got 0. Approximately 3. This is minimum 4. Among these 4 local minimums, we have to take the lowest value, that is called the global minimum. Okay, so in the classical algorithms, there is the possibility to stuck at the local minimum. Okay, the classical algorithms. But in quantum algorithms, right, it will form some tunneling approach. Right? It will find the global minimum without a need to climb. This is the path. This is the path called climbing up. Okay, this path is climbing up. Okay, from the down. So without need of climbing over them, it will try to identify global minimum by using the tunneling, quantum tunneling approach. This is one of the feature in the quantum optimization. One feature is superposition, another feature is quantum tunneling. And third feature is here interference. That means the circuit is designed to amplify the probability of measuring high quality solutions. Okay, so here M1 will be ignored. M1 means minimum 1. Minimum 1 will be ignored, minimum 2 will be ignored, minimum 3 will be ignored, and minimum 4 will be considered because this is the better solution, high quality solution, right? Then these three solutions, those solutions are called poor solutions or poor probability, right? So here we are amplifying the probability by measuring the high quality or more probability, maximum probability value, and by ignoring the poor probability value. So this is one of the feature we are using the quantum optimization approach. Based upon that, as we have seen, so many quantum optimization algorithms are there. So one of the optimization algorithm is here quantum approximate optimization algorithm, right? We will use those optimization algorithms in the logistics, finance, aerospace, and healthcare domain. Different domains are there. So here we will see the process of quantum approximation and optimization algorithm over here, right? So the first thing is problem encoding. That means whatever problem statement we are taking, the problem will be in the form of classical approach. Right. So the classical data should be transformed into the quantum information, quantum states. Okay, so for that, we have to go for encoding approach. That's what we are saying here, right? The problem encoding in the sense that the given data or problem is encoding into the quantum state. So the classical optimization problem is mapping into the cost Hamiltonian. So Hamiltonian is one of the matrix that is using Hermitian matrix. Okay, which is having the eigenvalues and eigenstates. Okay, eigenvalues and eigenstates. So eigenvalues and eigenstates which are having the information of quantum state about the energy of the quantum state, spin of the quantum state, those values. Okay, so this mathematical representation represents the energy of the quantum states, which is corresponding to the cost of the solution. Okay, cost in the sense total error. Okay, that should be minimum, right? So the goal is here to find the ground state. That means minimum energy to be spent. Okay, minimum energy to be spent to identify the optimal solution for our problem statement. That is the thing. We have to spend minimum energy. Okay, that is the thing. So for that, we have to initialize the qubits, right, at initial stage with uniform superposition. What that means? 50% of being in 0 state, 50% of being in 1 state, like that. Okay, so likewise, we have to use uniform superposition of all possible bit strings. Okay, which can be achieved by using the Hadamard quantum gates. Okay, so this is ensuring the algorithm starts by considering every possible solution parallelly, simultaneously. Okay, that is the thing. And we have to design the variational quantum circuit because it is coming under the variational quantum algorithm. So we are using the variational quantum circuits to solve this problem statement. By using quantum approximation optimization algorithm, the circuit is having a p number of layers. Okay, p number of layers. Each layer is having its unitary transformation. That means unitary matrices. Okay. So in that P number of layers, it should have combination of two layers, cast layer and mixer layer. Okay, cast layer and mixer layer. The cast layer is applying the cast Hamiltonian. That means which is encoding the classical information into the quantum information with the duration of this is represented by using the symbol gamma. This phase indicating the quantum states by labeling them into some good quality solution. Okay, that means it is calculating the cost with the minimum total error. That is the minimum cost. That is the good quality solution, right? And the mixer layer is having another Hamiltonian, which is having the sum of Pauli X gates with the duration of beta times. Okay, this is gamma times the above one cast layer. Okay, this one is with the beta times. Okay, so both cast layer and mixer layer both are available in the ansatz. Okay, in this the mixer layer is allowing the interference with each other. Okay, each other quantum states, which is moving probability from that poor solution to the optimal solution. Okay, that is the thing. So here, which is calculating the cost, then this is trying to identify the better solution by updating the parameters. Updating the parameters. So here, the gamma and the beta are the tunable parameters that can be updated by using the parameter shift rule by using optimizers like Adam or stochastic gradient descent like that. Okay, aim of this one is to minimize the cost, between that is cost means the difference between expected output and predicted output. Okay, so the difference between these two outputs should be minimized by using the this cost function, cost layer and the mixer layer. That's what. So this is the representation here given diagram. So initially we are passing the qubits and the information is transforming into the quantum states by using the Hadamard gate. So here we can add any number of qubit, Q0, Q1, Q2, etc. Hadamard gates are utilized. Then we are using two layers. One is the cast layer. That's what given over here with respect to jet gate. Okay, Pauli jet gate, right? That is the thing. And next one is here the duration gamma is used, gamma times. Okay, we can add any number of layers over here, which is having entanglement process also. And then we are using the mixer layer. Here, the mixer layer is using Pauli X gate. Okay, Pauli X gate here with respect to beta times, that is the with rotation angles theta. Okay, that is the thing. So finally, we have to measure the values, right? With the classical optimization approach, it is the classical optimization approach is based on, look like here. These are all two different approaches. That is the what you call maximization, minimization approach. Maximization, minimization approach in the mathematics. Because here we are talking about quantum approximation optimization algorithm, right? Here our aim is to minimize the cost. So this algorithm is almost look like a minimization algorithm by updating the parameters gamma and beta. Okay, that is the thing, right? Sampling in the sense we will get more number of candidate solutions. From this number of candidate solutions, we have to select the optimal solution. That's what I told you. We will get error like this. Okay, so if you get the error here, you will get one output also here. If you get minimum error here, you will get one best solution here. If you get one error here, you will get one output here. So this is candidate solution 1. This is candidate solution 2. This is candidate solution 3. Among this different candidate solution, we have to select the optimal candidate solution. That's what we are saying here. That process is called here sampling. Okay. So once you found best gamma and beta parameters, then using these parameters, you have to run the quantum, process the information over the VQC, then that will be your optimal solution. Okay, approximate solution. Okay, to the original problem statement. Right. So as I said, we can use this algorithm in different domain logistics. Here you can calculate the optimal vehicle routing by reducing the distance and spending, fuel reduction. That is the thing. And finance, mostly they will use in the stock market and investments, right, in any business. So there we can use quantum algorithm. Mostly the stock market, that is real-time data. So you need faster calculations. So quantum computing can be used in the real-time environment to faster calculation. And also in drug discovery. In drug discovery, okay. So the drug, we cannot, we have to add more number of ingredients. Ingredient 1, ingredient, item 2, like that. We have to add more number of ingredients. But each ingredient will have some percentage, 0.5 percentage, 0.02 percentage, 0.1 percentage, like that. So more number of items to be added, but we cannot identify the best combination, that is proportion. We cannot identify best proportion at the initial iteration. So we have to go for more number of iterations. There also we can use this algorithm, right? And the networking to identify the tower placements to minimize the interference. We can go for QAOA. So these are all. This is also one of the variational quantum algorithm. We can apply the variational quantum circuits. Okay, so this is the architecture, sample architecture I have taken from the literature. So initially we have to use the Hadamard gates. Hadamard gates. And before that, we have to define number of qubits requirement. Okay, you can start with the 3 qubits or 4 qubits or 8 or 10, like that. So you have to define your number of qubits required. Then you can initialize the values with the Hadamard gate. Why do we need Hadamard gate? Because Hadamard gate is introducing the superposition. Probability of 50% being one state, 50% of being another state. So superposition is introduced over here because one of the characteristics of the quantum bit is superposition. Okay, one of the characteristics of the quantum bit is qubit is superposition. So we can add the Hadamard gate. Then you can use cast layer here. The cast layer is used to calculate the to add some number of qubits. Okay, right. Right, number of number of gates to represent the quantum states. Okay, to calculate the cost, right? And after that, you see, this is with respect to the cast layer. This is with respect to the mixer layer. Mixer layer is using the X gates. Cast layer is using the Z gates and the entanglements. So you should know the process and the principles. Based upon that, you have to select the gates. Okay, to design the variational quantum circuit. Right. Again, this is another layer. This is another layer. Like that, you can add any number of layers. Then finally, you will measure the output over here. After measuring, then you can check what is the cost, right? If total error is more than your threshold value, then you have to go for updation of the parameters, the back propagation, but it is not look like a normal back propagation like a typical neural network. It is entirely different from the typical neural network. So we have to update the parameters by using the parameter shift rule. Then we can calculate, we can identify the output. Okay, so that is the thing. So this is the sample architecture I have taken from the literature, right? So with this, I will stop my session with respect to the various algorithms. Okay.
அதுக்கு தானே அந்த ஆர்கனுக்கு தானே டேட்டா வருங்க. கொஞ்சம் இது என்ன
So influx deep வச்சு போட்டு நம்ம வந்து
Hello, sir.
time series data
Sir, hello.
Sir, you may proceed, sir.
Yes, madam. That's it, madam. I have taken two variational quantum algorithms. One is the quantum circuits with respect to quantum neural networks, and another one is quantum approximation algorithm. So with this, I conclude the session. If you have any doubts, you may we will discuss.
Participants, if you have any doubt, you can post the doubts in the chat box, or you may unmute and talk. So 1 or 2 minutes may be given, sir.
Yes, madam. Yes, madam. Actually, participants can practice these algorithms in QUniverse platform or Qiskit platform, which is free only. They can practice whenever they are free.
Yeah.
Good afternoon, sir.
Yes,
Good afternoon,
madam.
participants. We sincerely thank the resource person, Dr. Kupusamy, sir, for delivering an insightful and engaging session on variational quantum algorithms for your valuable guidance, expertise, and the interactive approach benefited the faculty members and enriched their learning experience. Sir, we truly appreciate the time and the effort you devoted to making the session successful, sir. Thank you once again for your support and contribution, sir. Thank you so much. Dear participants, thank you for attending this FDP. We kindly request you to provide your valuable feedback by filling out the feedback form through the link shared in the chat box. Your feedback will help us to improve and organize more effective programs in the future. Kindly submit your feedback at the earliest. Participants are requested to proceed for lunch and rejoin the session shortly at 1:30 p.m. Thank you for your participation and cooperation. Thank you. Thank you, Ananda. Thank you, sir.
Thank you, madam. Thank you. Thank you to all the organizers and also coordinators and the audience who are bearing with me. Just I shared my knowledge, whatever I know in the quantum computing, and also I thank the management of RNK Engineering College for providing me the opportunity through the Dr. Saravanan sir. Who has invited me for sharing my knowledge with in the FDP. Thank you all.
Thank you so much, sir. You have given a lot of information. Thank you.
Okay, madam. Thank you. Thank you. Thank you.
So here, they also see here, the leading franchise is the registration. But the travel
A very good afternoon to everyone. Welcome back to the post-lunch session of our FDP. I hope the break has refreshed to you all. Thank you for rejoining on time. We are happy to proceed with the next session, and I encourage everyone to stay connected and gain maximum benefit from the expert insight being shared today. It's my great privilege to welcome our esteemed resource person for this section, Dr. P. Maliha, Professor and Head of the Department of CSE at NITTR, Chennai, and Adjunct Professor at National Institute of Technology, Meghalaya. Dr. Maliha is a distinguished educator with over 33 years of experience in teaching, training, research, and academic leadership. She has made significant contribution to advising technical education through innovation and excellence. She holds degree from University of Madras, Birla Institute of Technology and Science, Plia and Anna University, reflecting her strong academic foundation. Throughout her illustration career, she has coordinated over 350 faculty development programs. Delivering export session is more than 475 academic programs and contributed extensively to teaching training initiative at national and international level. She has also established innovative facilities such as the Extended Reality Lab and the Experimental Learning Technology Center while leading several digital education initiatives. Her research interests include data and text mining, cloud computing, e-learning, open educational research, and immersive technology. Today, she will deliver a session on implementing privacy mechanism. Oh, what a multi-talent personality. On behalf of our organization team and participants, I extend a warm welcome to you, ma'am. The session is yours. Thank you, ma'am.
Thank you. Thank you. Thank you, Dr. Akila. And am I audible?
Yes, yes, ma'am. Your
Yes.
voice is audible.
Okay. Let me share my screen. Okay. I have sent the request. I'm unable to share the screen. Yes. Hope my screen is visible.
Yes, ma'am. It's visible.
Okay. Very good afternoon, participants who have joined. It's a great learning for you for the past 3 days, I can say, from Wednesday onwards. Okay, and this is a very emerging new topic which many people would like to work, particularly on the research, right? So quantum computing, federal learning, and all those things, right? So the topic given to me to discuss is implementing privacy mechanism in federal learning. Okay, so let me just I would like to give my agenda. That is, we will have a quick review of what is federal learning and why privacy mechanism is needed, and what are the major privacy mechanism in federal learning, and what are the privacy attacks in federal learning, and what are the challenges in implementing federal learning, and particularly the federal learning frameworks. There are many frameworks which we can work and test it. Okay, starting from Google to Flower. Many people have 4 or 5 frameworks are available for us to work with Python and libraries and additional things. So I will be exposing that also. So any researchers would like to carry on the work on these federal learning environment, and what are the future direction, right? So this is the agenda for today's session. If you talk about federated learning, we know that data is born at the edge, not only the millions of phones and IoT devices constantly generate data, isn't it? My slide is visible, no? Dear participants, my slides are visible?
Yes, ma'am, it's visible.
Okay. So millions of phones and IoT devices constantly generate data, and the data enables better products and smarter models. So what is this? So you have so much of data generated at in our hands, I can say. So all the IoT devices, phones, and all these are generating so much of data. Fine. And then if you want to, so this data will hold immense potential for training powerful models. But, one second, this also I'll hide it. Right. So this data holds immense potential for training powerful machine learning models, but privacy concern often creates a barrier. However, we are using machine learning techniques to handle those data. Machine learning technique, you have large amount of data, and those data are in some cloud, and the privacy is an issue. So the federal learning comes into the picture. The federal learning emerges as a promising solution, enabling the training of AI models on a decentralized, this is where we have to note it down. It is all on the decentralized data sources. Okay, why? Oh, my internet is still. Okay. If there is any issue, please let me know. Okay, because I'm taking it from my home, and then it is giving some internet unstable. Okay, just tell me if there is any issue. I'll switch over. Okay, so it emerges as a promising solution, enabling the training of AI models on decentralized data sources without directly sharing sensitive information, right? And this approach is particularly beneficial for the applications in healthcare, finance, IoT, where data privacy is a paramount. So if you take what is this learning? It is a machine learning setting where multiple entities or clients collaborate in solving a machine learning problem under coordination of central server or service provider. Okay, each client raw data is stored locally and not exchanged or transferred. So instead, it is focused update intended for immediate aggregation or used to achieve the learning objective. So this is a definition which has been proposed in the advanced and open problems in federal learning. Okay, so it is a machine learning set only, but what is happening is where the multiple clients collaborate in solving a machine learning problem under the coordination of central server or service provider. So the main principle of federal learning is the raw data is stored locally. Okay, the raw data is stored locally, and what is exchanged is the models are exchanged and not exchange or transfer. Instead, the updates intended for immediate aggregation are used to achieve the learning objective. So if you take, all these machine learning approaches where multi-client collaborate to develop a joint model without ever exchanging their private local data. Okay, and if you look at it, it was been proposed by Google. This method addresses the difficulty of training AI models in environment where strict data privacy policies such as GDPR or HIPAA prohibits the sharing of sensitive information. So if you look at the applications, Like the applications are very vast and they continue to expand, particularly in healthcare. See, the federal learning can enable the development of AI models for disease diagnosis, personalized treatment, drug discovery, using patient data from multiple hospitals and clinics without compromising the patient privacy. See, you need a lot of data for healthcare and other things, but there is a danger on if we cannot let out the data like that. Okay, so the data privacy issue is there. So without compromising the patient privacy, how we are able to study how this model can be improved so that we can able to diagnosis, or we can give a personalized treatment, or a new drug discovery can be done. So for instance, the Google's federal learning for diabetic renotherapy, that is from the eyes, they are going to retina. Okay, they are detecting whether diabetic is will be there. Okay, that is, I can say they are going to predict. So the detections enable AI-assisted diagnosis using the patient data from multiple hospitals without exposing the sensitive medical records. Then if you take finance, see, in finance also it can be used to train the fraud detection models, credit scoring models, personalized financial recommendations using sensitive financial data from different users. Like MasterCard, for example, it leverages this federal learning to develop fraud detection models across different financial institutions, enhancing the security without sharing customers' transaction data. Then we can see that Internet of Things. So here the federal learning can enable the training of AI models for for smart phones, or I can say smart homes. Okay, wearable devices, autonomous vehicle, using data collected from devices without compromising the user privacy. You take this Samsung Smart Things, okay, which employs federal learning to improve AI-driven smart home automation by learning from the user behavior, but while maintaining the data privacy, right? So that is more important. You have to maintain the data privacy, but we need the data to train our model. And then the personalized assistance. So again, federal learning can improve the accuracy and personalization of virtual assistants by training them on a user data residing on their devices. See, for example, Apple iOS. Okay, that federal learning system enhances the Siri voice recognition capability by training the models on the user device. It doesn't go to the cloud at all. So if I'm using this iPhone, so what the voice, it gets trained on the local system itself. Okay, so the training models on the user device without the cloud storage of the voice data. So that is where the federal learning comes. So if you look at the core principle of federal learning, the fundamental is it relies on two principles: local computing and model transfer. So instead of aggregating the raw data into the central server for training, the model is brought to the data. Okay, so the typical process involves several steps. See, first thing is initialization and broadcasting. First step is initialization and broadcasting. So a central server initializes a machine learning model and sends it to the selected group of clients such as smartphone, IoTs, or edge servers. You can just look at this diagram. Okay, so that is the first step, right? Initialization and broadcasting. Then local training. Each client uses its own local data to train the model, optimizing it through the techniques like gradient descent. Then update the sharing. Clients send only the training parameters, the features, the parameters, like weights and biases back to the server rather than the raw data itself. Okay, so rather than the raw data itself. Then aggregation, the server collects and validates these updates, combining them to create a global model. This cycle repeats until the model reaches the desired performance level. So this is how the federal learning, and these are the core principle: local computing and model transfer. Okay, so when you look at this architecture, so there are two types. Okay, the way the federal system is structured fundamentally changes its privacy profile. One is the centralized federal learning, another one is the decentralized federal learning. So when I talk about centralized federal learning, it relies on the central orchestra to manage to update. So privacy mechanism here focus on protecting data from the server itself or from the external airdrops, right? And for the decentralized federal learning, mostly this blockchain enabled. Okay, it eliminates, since it is decentralized, it eliminates the central server and it avoids one point of failure, that is single point of failure. And these system often uses smart contracts and consciousness, that is the mechanism to validate the model updates, ensuring that only honest contributions are accredited into the global model. Then the overhead costs are there. Privacy mechanism often increases communication cost due to the encrypted packet value sizes and computational cost due to the complex encryption and decryption cycles. Okay, and then if you look at it, yes. So when you look at architecture, it is centralized and decentralized. And the federation scale, again, you have two types: cross silo and cross device. So cross, that is, it involves a massive number of mobile or IoT devices, while that is for cross device. For cross silo, it typically involves a smaller number of high capacity organization like banks or hospital or institutions. So that becomes the cross silo. Cross device means it is a number of mobiles or IoT devices. Okay, so that is another type, cross silo or cross device. So silo will be on number or maybe big organization. In that organization, you get a lot of data. Okay, so you will have smaller number of higher capacity organization. Here, number of devices, cross device, and then what? If you look at this data distribution, again you have, it depends upon how the data is split across the features and sample phases. How do you split for testing and for training? It is categorized as horizontal, similar attributes, different users. Then for vertical, it is different attributes, similar users, or it can be federated transfer learning. So this is the general things. Okay, so you could have already done or learned about this in the past few days, right? Okay, so this federal learning provides several key benefits, right? One of the biggest advantages is the enhanced privacy and security. As raw data never leaves the local devices, significantly reducing the risk of breaches or unauthorized access. So then federal learning reduces the data transfer and communication overhead by minimizing the need for large-scale data transfer to centralized repository, because we don't do that. Okay, no data transfer is done. So in that case, yes, it reduces the data transfer and communication by avoiding the communication overhead, by minimizing the need for large-scale data transfer to centralized repository. That is the second one. And it reduces the bandwidth usage, of course, bandwidth usage, and it also improves the efficiency. So another benefit of federal learning supports compliance with data regulations such as GDPR and HIPAA or CCPA by processing data locally and reducing the need for complex compliance strategies. Okay, so with this, federal learning allows personalized AI models, enabling training on user-specific, what do you say? User-specific data for more personalized and context-aware AI experience without compromising the privacy. So having seen these benefits like privacy and security, reduces the data transfer and communication overheads, and it is compliance. It is also taking care of the compliance with the data regulations things. And then it is we are also able to provide personalized and context-aware AI experience without compromising the privacy. If you look at the benefits of it, so the primary advantage of federal learning is the ability to balance the performance and the privacy. So it allows for collaborative training across diverse data sets, which improves the model generalization and fairness while maintaining their data sovereignty. However, it faces several challenges like, of course, you have the communication cost. That means that transmitting model updates several millions of devices can be resource sensitive and can be affected by the unreliable network connections. Then system heterogeneity, okay, variation in hardware, software, and then power across devices can lead to inconsistency in training. And then we have the security risk also. Despite its primary focus, this federal learning is still vulnerable to honest but curious servers, gradient information leakage, and poisoning attacks, where malicious clients submit faulty updates also. So these are the benefits. And of course, for a benefit, you have the challenges. The challenges is the communication cost. Transmitting model updates across millions of devices can be resource intensive, affected by unreliable network connection. Then what is the benefits? Yeah. So challenges, this is okay. See, here, the challenges is, primary challenge is the communication efficiency. I think this, okay, I will explain this. Communication efficiency, as frequently model updates strain network resources, particularly in mobile and IoT applications. Like techniques like model compression, sparse update can often mitigate this issue. Another challenge is the heterogeneity, that is in data and devices, where variation in processing power, connectivity, data distribution make training complex, and they may lead to biased model. Then federal learning is also susceptible to security threats and attacks such as poisoning attacks, advisory model updates, inference attacks, which can compromise the model integrity. So the model aggregation and performance optimization remain ongoing research. And it is an ongoing research challenge, as efficiency aggregating updates without performance trade-off is still being explored. Okay. So this is where the benefits and challenges. It is also a benefit and it is also a challenge of it. So yes, now the privacy, what are the privacy techniques in federal learning. You could have learned about in the second day or something like that, right? Privacy techniques in federal learning protect sensitive data during the decentralized model training, where raw data remains on local devices and only updates are shared. Okay, so that is the core principle of it. So what are the different methods here? So the different methods include differential privacy, that is adding noise addition, Gaussian noise, or so noise can be added to it. That is, one is the differential privacy. The second is the secure multi-party computation. Okay, so that we call it a secure aggregation. And then we have the homomorphic encryption, that is calculation based upon the encrypted data. So here, privacy preserving federal data. Here it is a collective machine learning paradigm designed to train models across decentralized data storage while ensuring that sensitive information remains secure and private. So if you look at it, what is it? The privacy preserving federated learning. Okay. So the key aspect of privacy include the regulatory drives. Okay, you know what are the regulatory drives? You know? Okay, the regulatory drives like GDPR, that is, it is by EU, that is European Union. It prohibits the use of personal data without explicit consent. Okay, and then you have, what are the other regulatory drivers apart from GDPR? You have HIPAA. So that is the United States. Okay, it prevents healthcare, particularly the healthcare providers, from sharing sensitive data, sensitive patient data or records, I can say. Then you have the other one is apart from GDPR and then HIPAA, we have this PDPA, that is it is Argentina, and then I had a slide. So then you have the PDPA, that is Argentina, and APPI, that is Japan. That is the national laws that restrict, govern data privacy in their respective region. So this privacy preserving federal network, the key aspect is, first is the regulatory drives. Second is the specific vulnerability, privacy vulnerability is there, right? Despite not sharing the raw data, federal learning remains susceptible to several type of information exposure. So what are they? Like the gradient information leakage, like stored model updates can inadvertently relieve data about the local training samples. And then we were talking about this honest but curious service. So what does it mean? A central server may attempt to interfere private training data from the gradients it receives for aggregation. Okay, and then you can also have the inference attack. So malicious actors may use techniques like membership interference, determining if a record was in the training set, or it can be a gradient intervention, reconstructing the training samples like this. Okay, so yeah, yes, I have. Despite not sharing the raw data, federal learning remains susceptible to several types of information exposure. So one is the gradient information leakage. Another is the honest but curious servers. A server may attempt to interfere, infer private training data from the gradients it receives for the aggregation. And then the inferences attack, like malicious actor may use techniques like membership interference, determining if a record was in the training set, or the gradient intervention inversion, reconstructing the training sample itself. Okay, so these are the different things. And the third one is the privacy enhancing techniques, or these are called the mechanisms. Okay, the sources identify or you can say four different or four primary technology approaches. So if you look at the literature review of this privacy enhancing technologies, so I was able to pick up these four methods. Okay, so what are those things? One is the referential privacy. That is, it involves adding mathematical noise, that is the Gaussian or Laplacian to data or gradients to ensure that the individual record represents does not significantly alter the output. So that is the one. And the second one was the homomorphic encryption. So a cryptographic method that allows a server to aggregate updates while they are still encrypted, preventing the server from ever seeing the plain text data. So I have not given any mathematical equation. I have just I'm just telling what are the different methods available. One is the differential privacy, where it is adding mathematical noise to the data or gradients to ensure that the individual record presence does not significantly alter the output. Then the second is the homomorphic encryption. Here, a cryptographic method that allows a server to aggregate update while they are still encrypted. So preventing the server from ever seeing the plain text data. Then the third is it secures multi-party computation, that is SMPC. Here what happens, it uses the techniques like secret sharing or pairwise masking so that the participants can jointly compute a global model without disclosing their individual input. This is another method for implementing the privacy technology. So what does it mean is, it means that, yeah, one second. So this approach, it will enable participant to jointly compute a function on their input while keeping those input private from the another. So what are the common techniques will be secret sharing and pairwise masking, which will prevent any single party, including the server also, from accessing the complete data set or raw updates. Okay. And then the next one is the anonymization. That is, it involves removing personal identifiers, personal IDs from the data set. While simple and efficient, if you remove some personal IDs, there was one example also. In a photo, if you are a photo has been taken, that was one image in the data set. Okay, so in that image, let us say you do not know who is driving that car and all those details. Okay, no photo of any person on the road, but there are two big cars on the road. So we can think that, okay, there's no person, there's no personal identification tracking who is doing that. But what happens, there may be, this is a use case I'm saying, that is a very old, that is very famous and very popular old car. And it has been redesigned and it is available in the road. So from that, they can pick up, maybe in the world, there are around few people, okay, particularly the place, if they know, okay, if they know the place can be identified from the image. From the image, the place can be identified, and from the place, who's having that particular car can be identified, and the person can be identified. So we might think, okay, if you remove the personal ID, that means you are removing it. It is not like that. It may look simple and efficient also, but it is often considered inefficient or insufficient for complex statistical queries, and it is frequently used alongside with robust methods like DP, okay, like your photos and other things. Fine. So here the there are another one is also there. So most of the methods which I was able to pick up in the literature review, particularly in the privacy enhancing technique, is one is the differential privacy. So in differential privacy, it is a method which is mostly used technique, okay, involving the injection of noise. Okay, so the differential privacy is one of the most widely used technique, you can say, which involves injection of noise, typically the Gaussian or Laplacian noise, into the data or gradient. So it will ensure that addition or removal of any single data record does not significantly alter the algorithm output, thereby preventing the re-identification attacks. Okay. However, there is an inherent privacy utility trade-off, as increasing noise to improve privacy can diminish the model accuracy. So when you go on for the performance metric, then there will be a trade-off. So if you keep on increasing to hide the privacy, then the accuracy may be a thing. Okay, that will be an issue. So there should be a trade-off. So one is there, but simple but efficient, by adding mathematical noise on Gaussian or Laplacian to data to ensure that the individual record presence does not significantly alter the output. And then the second method is the homomorphic encryption. So this is the cryptographic method. Okay, this cryptographic method allows a central service to perform the mathematical operations. What type of mathematical operations? It can perform aggregation on the encrypted gradients without even decrypting them. So while highly secured against honest but curious server, that is, it is on the servers, no? So then this HE, can impose a significant computational overhead, because you are putting that method and it is performed, the mathematical operations aggregation method is performed on the data in the server. Okay, so it can impose a significant computational overhead, particularly as model complexity and number of gradients increases. And the third one is the secure multi-party computation, that we call it as SMPC. So this approaches enables participants to jointly compute a function on their input while keeping while keeping those input private from one another. So common techniques will include secret sharing, pairwise masking, which will prevent any single party, including the server, from accessing the complete data set or raw updates. So then we have also discussed the anonymous. So these are the four privacy enhancing technology or mechanism used. So, okay. So this is what I was talking. So one is the differential privacy DP. Okay. So there should be a trade-off. There will be a trade-off. A lot of noise is there, and so the accuracy will be diminished. And for homographic, so here the encrypted gradients will be there. So a lot of computation aggregation is there. So computational overhead will be on the server, will be there. Okay, and this will here what happens is the common techniques which includes secret sharing or pairwise masking, which prevents any single party, including the server, from accessing the complete data set or raw updates. Okay, and then this was removing the personal identifiers from the data set. While simple and efficient, it is often considered inefficient for complex statistical queries and frequently used alongside with the robust method like TP. Okay, now what are the challenges, right? Whenever you are evaluating, no, there are a lot of what are the metrics you have seen. So evaluation and metrics, if you see, privacy budget is there. So in differential privacy, a smaller indicates a stronger privacy protection. And resistance to attack is these systems are tested against this poisoning attacks where malicious clients submit faulty updates, or that is the poisoning idea. So malicious clients submit faulty updates. And then interference attacks are where attacks try to deduce private data from the global model. Okay, that is called interference attack, where the attackers try to deduce private data from the global model. Okay, so if you take this one, challenges, what are the challenges in data privacy mechanism is, one is the computational complexity. Okay, the encryption and the cryptographic method increase processing time, and the communication overhead is the frequency encrypted communication increases the bandwidth usage, and then accuracy versus the private trade-off. So higher privacy often reduces the model performance. Scalability, that is managing thousands or millions of clients, is difficult, and heterogeneous devices, different devices capability affect training consistency. Okay, now comes the federated learning framework. Okay, so how many people, just I would like to ask, I'm talking to, right? Have you worked on any framework um, or any models so far on federal learning? If you have done it, just put it on the chat so that it'll be nice. Dear participants, are you with me? So we were discussing, or I can say it was a review of what you have done, right? So what is federal learning? And particularly we were talking about only the privacy, okay? What are the benefits? What are the challenges? Even though we go in for federal learning, we say, okay, we are going to minimize the privacy. Still, in this method also, in this federal learning method also, there is a privacy concern. Okay, if you want to work on these federal learning, what are the frameworks you have been using or you have known? Yes, participants, what are the framework you are aware of it or you have been exposed to it so that you can work further for in your research or in your for learning purpose or for research purpose, you can do it. Can you just type in your chat box, or somebody can unmute also and say, am I audible?
Yes, ma'am. Yes, ma'am. You're audible, ma'am.
Okay. Here also my here unstable, it is coming. So I'm so worried. Okay. So, okay, I do not know Saturday afternoon session, whether people. Okay, let me introduce whoever is interested, they can do. See, there are several frameworks available where the data set is available and the methods are available. Python libraries are available where we can work on it and test it, and we can also do some research, and then with different data set or with different methodology, or we can also devise algorithms to that. So first we can learn and then we can go for the next thing. So if you look at it, yes. See, where you will be working is like in healthcare, some like I have worked on flower. So there you have the images, okay? So maybe the data set for working is different, but we can have our own data set and then work on it, right? So you can work on healthcare, you can collaborate with some hospital if the hospital allows you to do. So then on disease prediction, you can work cancer or heart disease. On the first day, Hemlata, like Dr. Hemlata says, she was working on cancer, breast cancer. So you can also use this Federal method. She was using quantum machine learning, right? But whether the data, that is very important. And the image, medical image analysis without sharing sensitive patient record, that you can do it. Then IoT and edge computing. So real-time anomaly detections like devices like smart watches, industrial sensors, while maintaining the data sovereignty for the users. Then, of course, the NLP. That is my favorite things. Okay, so applications like Google Gboard uses the federal learning for personalized text prediction. So in your mobile also, or whatever, wherever it is. Okay, while ensuring user keystrokes, which will never leave the device. Okay, it will not go to the server at all. All those things, training and things are model is being local computing is being done. So to start working, okay, so first I'll tell what it is. So these are the federal learning frameworks. One is the TensorFlow Federator, that is TFF, which is being developed by Google. And first I'll explain and then I'll show you. Then we have the PyCFI, that is it's part of the open-minded ecosystem. Okay, a part of the open-minded ecosystem. Yeah. See, the first one, no, the TensorFlow Federated, I said it is developed by Google, and it is an open source framework for machine learning and other computation on decentralized data. So it will integrate with TensorFlow, and it is excellent for simulating the federal building, training and building new federated learning algorithms that you can use it. Otherwise, the second option or second available. There are different. These are different things. Okay, it is a part of open-minded ecosystem. It is a Python library. Okay, PySci-Fit. Okay, you pronounce it in your way. Is a Python library focused on the privacy preserving AI. Okay, it enables what it does. It enables a federal learning and works with the popular deep learning frameworks like PyChart, PyTorch, and TensorFlow also, supporting techniques such as differential. So you can test it how the differential privacy and secure multi-party computation. The first and third can be tested on this one. And the third is the Flower. Flower is a framework, flower.ai or Flower is a framework, okay, and it is highly customizable framework for federal learning. So it works with many machine learning libraries, including the PyChart, TensorFlow, Scikit-learn. So all the library support is there, making it versatile for the teams with diverse machine learning stacks, okay. And then the next we have the NVIDIA Flare. So in NVIDIA Flare, this framework is designed for medical imaging and genomics, enabling collaborative AI development in healthcare. It is also used in applications like autonomous vehicle. Then FATE is there. It is developed by VBank. FATE is an enterprise-focused platform that supports federal learning with advanced privacy techniques like homographic encryptions. Okay, that is the second. It offers a web-based interface for managing the workflows. Okay, and then Substra is there. It is for the multi-partner medical research project. It is now hosted by the Linux Foundation. It is particularly strong in medical field, emphasizing the data ownership, privacy, and traceability. Okay, so these are the federated learning frameworks are available for us to work and test with all those privacy techniques. Okay, so yeah, before that I will also I will show once again. I will share my screen. You are able to see my screen? That Google Cloud is there?
Yes, ma'am. It's visible.
Yes. See here, you can see that you can have this one, Google Hibernate Engine. Okay, the first one what we saw was TensorFlow Federated, no? So TFF. So you saw the first one, no? TensorFlow Federator. It's an open source framework developed by Google and can be used for building and simulating federated learning models, allowing developers to experiment with and implement federated learning algorithms within the cloud ecosystems. Okay, so this is, if you click on it, like everything is available. The API, the Python programming. So you have to understand it. Like here, the first and third model for data privacy is also available. Okay, so the TensorFlow Federated is an open source framework. It is an approach of machine learning. So this, what is it? So the API, this layer offers a set of high-level interfaces that allows developers to apply the included implementation of federated learning and evaluation to their existing TensorFlow model. And then the federated core API is also available, and the things, what is it? You can have. And I will share this link so that you can note it down, or you can search also. This is for TTF. Okay, where it is, chat. Right, because when you want to work on it, it'll become like a workshop where you have to do it. Okay, so people who are interested on it, you can carry on with this. Okay, TensorFlow Federator. This is by Google, and it gives you the federated learning and other things, right? So I've shared the link. So you have all those things, and you have the demos also. Okay, you have the federated learning workshop using TensorFlow. So you can watch the video, and the code is given, and we can try on it. Okay, so this is one of the federated learning framework. Okay. Without centralized training data, and then federated analytics is there. Okay, collaborative data science without data sanction. So you have all these things. So in GitHub, you can have, okay, so this is a training models and all those things. Here, I have not worked much, but I can show you another one where I have practiced on this one. So this is the flower framework. Okay, flower. You can also, I can also share with this. This is for the learning, and other one is for the model. So this is This is the tutorial available, and also the model framework is also available. Okay, so I have shared this one. Okay, so here what it is, the classical machine learning, how it is different from the federal learning, and then challenges of classical machine, regulations, federal learning, centralized, and all those things. Okay, you can have, Aram say you can work on it, right? So this is the learning part. Actually, the federal learning, another one is there. Here in GitHub, you have this lab. Okay, I'm sharing this one. This is where you can get all the docs. Where it is. Because it is in my login. Okay. Right. So here you have that flower. Okay, this flower is a framework, and it is a highly customizable framework. Okay, for federal learning, it works with any machine learning library, including the PyCharm, TensorFlow, Scikit-learn, making it versatile for the teams to build it. Okay, so when you want to work on it, so what is the thing you have to do is, so when you want to start working with Flower for federal learning, you can follow the steps. Okay, so it is also demonstrated in the tutorials also. First is the environmental setup. You have to ensure that you have a clean Python environment. So you can install the framework using the so first you have to install Flower. Okay, so for that you have to have an environment where you can have clean Python environment, and then you can say pip install Flower. Okay, and then if you click on it, it will say pip install Flower. Anybody who wants to try, you can do it. Okay, then after that, after installing it, you have to create a project, and then using the Flower new command in your terminal, you can interactively guide. It will interactively guide you through the setting up a project, including selecting your preferred machine learning framework, whether you want TensorFlow or JAS or something like that. And then you have the core component, you can have now the Flower will have two things. Okay, that is two main parts. One is the client application, another one is the server application. So in client application, it will define how the model is trained locally on the participant data. Okay, so locally how it has been trained on the participant data. You can implement fit and then evaluate methods within the class. Okay, and then the server application, it will manage the aggregation strategy, such as it has many functions already been defined, like fed average. Okay, that is, it will handle the sampling of nodes and orchestra the rounds of training. So it is all built upon the convolution neural network. And then running experiments, like once your code is ready, use the flower run command to execute you can have the quick start tutorial. That one. Here you have this. Okay. So pip install, then quick start, then choose a different strategy. So here you have the local model and the global model. So this is a client side thing. You have the server side. Okay. Right. So here for data, what happens is here is you can utilize this flower data set library to handle the data partition efficiently. So that is actually what they are doing is they are in this tutorial they are using a data set called CIFAR, CIFAR 10. Okay, so they are using that data set for the demonstration, and if you look at it, it can explore. That is, it can expand, and you can explore the official flower documentation and the community-driven baselines available in the GitHub repository. So if you go to this GitHub repository, you can just see all these. See, the data set is there. Okay, and what it is the images classified with the animal images classified. Okay, so they have all these examples and those things available. Hope I'm audible, right?
Yes, ma'am. Audible.
So you can see that in this tutorial they are using all these frameworks. No, see, it is a very good framework. Different machine learning framework having different strength. Hope you're okay. You can also open it from your side. Okay, so it works with all these pie chart, TensorFlow, Hugging Face transformation, all your Python things are working. So JAS is also there for federated robots. For pandas, you can use it for analytics. For raw NumPy, all these are there. And then so how do you use all those things are there? So if you want to work on different sets, you can use different things, right? So it is one learning. This I have used. Okay, it is very nice. And then you have a video also. They have a 2 hours video. It is there where they are demonstrating how to build. Okay, so this will be helpful for you if you are very new to it. It will help you to learn and use all these things. So if you look at the demonstration, they are using a data set which is having classifying the animals like that. Or if you want to work on something else, you can work on Hugging Face also. So it is a collection of community contributed projects that reproduces the experiment performed in popular Federated learning publication. So the researchers can build on flower baselines to quickly evaluate new ideas. The flower community loves contribution. You can also make it visible. So there are a lot of things available. I hope I have shared the link to you. Okay. See, like how from centralized to federated. And then there are so many examples also, vertical federated learning, right? So particularly you can work on it. And this is the GitHub, and then samples have been given, data sets have been given. Okay, so I have shared this one. And if you have, when you're working, if you have any issues also, you can post it and the issue will be resolved. Okay, so this is for working, and for learning, you can have this one. What is it? That Federated, that is Flower framework. What it is? What is Federated learning? How to get started with Flower, and then you can use the Federated learning strategies. Okay, so are you able? Somebody trying or just opening at least? My links are working for you. So this is what? This is the, see here, this is the data set. Okay. So 10 different animals they are categorizing, that data set is there. So they will evaluate the model data set and return the evaluation metrics. So that is, so its sample is available. With that we can work. And how do you want to split? Like the data is available like vertical split, or what model you want to work. You can work on different models and get different outputs also. Okay, so the link I think is there. If you go back to the, this is what, like hope my screen is visible. So TensorFlow, we saw that this is why Google. Okay, this Flower is a one which I showed. Okay, there are other things also. NVIDIA has, then Federated AI Technology Enabler has Substance. I haven't worked on it. I'm just sharing because I am like past 6 months I'm working on it along with my one of my scholar. Okay, so this is on the Flower. We are working on it. Okay. So if you look at the future of federated learning, yeah, this field is rapidly evolving, and the current research focus on addressing its challenges, such as improving the robustness to the data and system heterogeneity, developing more sophisticated privacy preserving techniques, creating more efficient communication protocols, and enabling truly personalized federated learning experience. Okay, so if you look at it, yeah, the future directions are how it is working. So as AI is also a part of it, how you can combine privacy with explainable AI. So explainable privacy aware federated learning. Okay, after learning the federation, you can go for this future things. And then how can we use blockchain for trust and decentralization? So blockchain based federated learning can be done. And then since many people are interested in quantum, okay, so how quantum safe cryptography can be there. So preparing federated systems for quantum computing threats. And then AI driven adaptive privacy. So dynamically adjusting the privacy level based upon the risk. So first, once we are able to work on the existing federated systems, then understanding how it works, getting the proper data. After working on it, we can expand it to these new things, like how we can have a hybrid with the, or not an hybrid, how we can go further with explainable AI or blockchain based federated learning or quantum safe cryptography or AI driven adaptive person. So since all these things are growing, lot of community help is there. We can also contribute, and you can also learn from that community So you have to first become a member. When you're using this Flower, no, you have to become a member. It is all free only, it is open only. Okay, so putting, becoming, just signing it up and learning. By learning, you can have some questions on it. If you're not able to do it, you can query the community and they are ready to help. Okay, and so these are the references I referred. So Google AI blog on Federated Learning, then survey of Federated Learning. This is a research paper which gives you the full survey of what are the methods used, particularly in data privacy. And this Flower.ai docs framework tutorials is also there. Okay, so yes. We have seen what the mechanism, particularly in Federated Learning, the privacy mechanism, and how you can implement it. So for implementing, I have shown some of the Federated Learning frameworks. There are at least, to my knowledge, there are at least 6 frameworks available. There may be more also, but 2 of the frameworks I have put my hands on it. One is the Google one, another one is the Flower AI. Okay, so the other I haven't done it. Okay, so but there are available. Somebody who's interested can go work on it depending upon the your interest and other things. So I'll stop here. Okay, if you have any questions, we can discuss, or if I want to share something. Chat. Okay, there's something. Yes, madam. Yeah. Yes. So there are even the Python programming, how to step-by-step instruction is also given, and there are details how to split the data into training data and other things, and what models can be built upon. All the step-by-step procedures are given, so you can just follow it up and then test it. So once if you work, the method, the algorithm or the method, you can remember. So we have done the privacy, particularly how to work on the privacy and the metrics also. See, you have to, after then, how to measure. The metrics is very, very important, isn't it? How do you measure that? What is the metrics used to measure? So one method which I have left is trusted execution environment. I just told 4, but that it provides a hardware level security. Okay, so I just left it. So the 4th method which you can test it to these frameworks is available, so you can do it, right? So that is what I would like to say. So applications, you can either take disease prediction or medical imaging or patient monitoring on healthcare, you can say. Or you can also work on finance, fintech, like fraud detection, credit scoring, and other things. Smart devices is personalized assistance, like a keyboard prediction, and then recommendation system. If you look at education, okay, we look at because we work on engineering education, we look at on how it can be used in the education sector for personalized learning analytics and student performance prediction. So students' performance prediction, that is also one good thing which we can do it. All right. So if I want to conclude it, let me just say. So federal learning significantly, what it says, enhances the data privacy by decentralizing the training. Okay, it is not centralized; it is decentralized the training. However, privacy risks still exist. So only we are learning about the implementing the data privacy in federal learning. And so why we are not going for machine learning, we are going for federal learning. Well, because we are decentralizing the training, but still the privacy risk still exists through models which can update what do you say for the risk can be, or data privacy can be through the model updates or communication channels. So implementing mechanisms we saw, one is the differential privacy, then what is the other one? Secure aggregation, and then homomorphic encryption, and then SMPC. That is, these are the four, or even in the literature, if you see, they also tell about the trusted execution environment, but particularly it is on the hardware side. These all provide a strong protection against the attacks. So a hybrid combination of these techniques is increasingly becoming the preferred strategies for building secure, scalable, and trustworthy federated learning system in healthcare, finance, education, and smart technologies. Wherever the data is very, what do you say, need to be secure. It should not be, the privacy should be maintained, no, for sensitive data. In that cases, these federal learning data privacy mechanisms can be used. So we saw different learning platforms, frameworks, not framework. And one of the framework is the Flower AI, where you can go and test it. I have shared the link, the GitHub. So with this, I'm just concluding my presentation, right? Let me stop where it is. Am I presenting? Stop. Okay, fine. Okay, this is like an intro to your data privacy mechanism in federal learning. Okay, no questions.
Yes, ma'am.
Yes.
Yes, ma'am. We will open the floor for participants set questions, ma'am.
Yes.
Yes, dear participants, do you have any queries, questions?
Actually, they have to work on it, right? And then all the tutorials and the help is available on the frameworks. On I have shared the 6 frameworks. Yeah, it is. They should be.
Everything is available on the chat box, ma'am.
Yes.
So, dear participants, any queries? If suppose you are having any
Anybody
queries,
is working on this, or I will ask anybody working on this federal learning with the quantum or with the blockchain or with explainable AI. I would like to know, and I would like to interact.
Madam, we are doing research.
Yes, good.
We are doing on federated learning involving organ transplantation. Organ transplantation. So here the data set was obtained from UNOS. UNOS is
Okay.
a United Nation-based organ transplantation organization. From there, we have obtained the data set and we are working on it. We are using a framework called DeepServe.
Okay.
We are using a
Deep,
framework called
deep,
DeepServe.
deep serve.
DeepServe.
Serve.
Deep
Okay.
SERV.
Okay, that's a different framework apart from these six.
Yeah.
Okay, okay. See, this is nice.
DeepServe.
No, if you discuss, we can come to know.
Yeah.
Yes.
But that is that DeepServe, we are using it for identifying the survival fitness, because you can do the organ transplantation, but at the end of the day, how long he is going to survive after the transplantation has been done.
Prediction. Okay.
So predicting part that
Okay. Right.
sorry,
Good, sir.
DeepServe takes.
Very nice to hear. And it's a very sensitive thing, no? Sensitive area.
Yeah. So yeah. So we are bringing in three concepts there. One is the federated learning. Number two is the blockchain concept, and the third one is the DeepServe framework.
Okay.
Because the organ data set basically is a very confidential thing,
Yes.
and highly sensitive thing, which many of the organization doesn't share.
Okay.
So that's the reason why we wanted to try this one.
So you belong to which institute, sir? Where are you working? From which?
I'm from PMC Engineering College, Hosur. PMC
Hosur.
Tech.
PMC
Hosur,
Tech.
yeah.
Okay. Wonderful. Nice to hear from you.
Thank you, ma'am.
Right.
Yes, participants, any other queries?
You can share your thing also. So people, we are all working on it. We are all learning and working on different areas. Okay.
Yes, ma'am, we conclude. Yes, ma'am.
Okay, ma.
Yeah,
Okay,
yes, ma'am.
right.
Yes,
Thank you.
actually, we need to thank ma'am. Yes, ma'am. On behalf of our organization team and all the participants, I extend our sincere thanks to you, ma'am, for delivering such an insightful session on that implementing privacy mechanisms. The presentation was highly informative and provided us with valuable knowledge and practical insights into this important domain, ma'am. The clarity with which you explained the concepts made this session both engaging and enriching for all of us, ma'am. So your vast experience in teaching, research, and technical education was clearly reflected in today's session. So, and we are truly grateful for the time and effort you have taken to share your expertise with us, ma'am. So, we sincerely thank you for your valuable presence and making this session meaningful and impactful. Once again, thank you so much, ma'am. It was an honor to have with you as we wish you
Thank
continued
you,
success.
ma.
Yes,
But
ma'am.
thank you for your kind words.
Yes, ma'am.
But in this area, I am still learning. Okay,
Yes, ma'am.
here I'm learning, and then like we are all co-learners.
Yes.
Yeah, particularly in this area. Right. Thank you
Thank you so much, ma'am. And for participants, so we have already posted today's feedback link on chat box. So we kindly request you everyone submit that feedback form. Once you have submitted means you kindly leave the meeting. Thank you so much. So today's program we have concluded. Thank you for your valuable participation and support.
Do we have class tomorrow, man?
Yes, sir. Tomorrow you need to join the same link at
Okay.
8:55 a.m. itself because we have session at 9 a.m. So you need to join on same link. Thank you so much, sir.